Chapter 5. Bend or break. Life doesn't stand still. Neither can the code that we write. In order to keep up with today's near-frantic pace of change, we need to make every effort to write code that's as loose, as flexible as possible. Otherwise we may find our code quickly becoming outdated, or too brittle to fix, and may ultimately be left behind in the mad dash toward the future. Back in Topic 11, Reversibility, we talked about the perils of irreversible decisions. In this chapter, we'll tell you how to make reversible decisions, so your code can stay flexible and adaptable in the face of an uncertain world. First we look at coupling, the dependencies between bits of code. Topic 28, Decoupling shows how to keep separate concepts separate, decreasing coupling. Next, we'll look at different techniques you can use when Topic 29, Juggling the real world. We'll examine 4 different strategies to help manage and react to events, a critical aspect of modern software applications. Traditional procedural and object-oriented code might be too tightly coupled for your purposes. In Topic 30, Transforming Programming, we'll take advantage of the more flexible and clearer style offered by function pipelines, even if your language doesn't support them directly. Common object-oriented style can tempt you with another trap. Don't fall for it, or you'll end up paying a hefty Topic 31, Inheritance tax. We'll explore better alternatives to keep your code flexible and easier to change. And of course, a good way to stay flexible is to write less code. Changing code leaves you open to the possibility of introducing new bugs. Topic 32, Configuration, will explain how to move details out of the code completely, where they can be changed more safely and easily. All these techniques will help you write code that bends and doesn't break. Topic 28, Decoupling. When we try to pick out anything by itself, we find it hitched to everything else in the universe. John Muir, My First Summer in the Sierra. In Topic 8, The Essence of Good Design, we claim that using good design principles will make the code you write easy to change. Coupling is the enemy of change, because it links together things that must change in parallel. This makes change more difficult. Either you spend time tracking down all the parts that need changing, or you spend time wondering why things broke when you changed just one thing and not the other things to which it was coupled. When you are designing something you want to be rigid, a bridge or a tower perhaps, you couple the components together. Images links 01.png. The links work together to make the structure rigid. Compare that with something like this. Images links 02.png. Here there's no structural rigidity, individual links can change and others just accommodate it. When you're designing bridges, you want them to hold their shape, you need them to be rigid. But when you're designing software that you'll want to change, you want exactly the opposite, you want it to be flexible. And to be flexible, individual components should be coupled to as few other components as possible. And, to make matters worse, coupling is transitive. If A is coupled to B and C, and B is coupled to M and N, and C to X and Y, then A is actually coupled to B, C, M, N, X, and Y. This means there's a simple principle you should follow. Tip 40 for decoupled code is easier to change. Given that we don't normally code using steel beams and rivets, just what does it mean to decouple code? In this section we'll talk about train wrecks, chains of method calls. Globalization, the dangers of static things. Inheritance, why subclassing is dangerous. To some extent this list is artificial. Coupling can occur just about any time two pieces of code share something, so as you read what follows keep an eye out for the underlying patterns so you can apply them to your code. And keep a lookout for some of the symptoms of coupling. Wacky dependencies between unrelated modules or libraries. Simple changes to one module that propagate through unrelated modules in the system or break stuff elsewhere in the system. Developers who are afraid to change code because they aren't sure what might be affected. Meetings where everyone has to attend because no one is sure who will be affected by a change. Train wrecks we've all seen, and probably written, code like this. Public void apply discount, customer, order underscore ID, discount, totals equals customer.orders.find, order underscore ID, dot get totals. Totals.grandtotal equals totals.grandtotal, discount, totals.discount equals discount. We're getting a reference to some orders from a customer object, using that to find a particular order, and then getting the set of totals for the order. Using those totals, we subtract the discount from the order grand total and also update them with that discount. This chunk of code is traversing 5 levels of abstraction, from customer to total amounts. Ultimately, our top-level code has to know that a customer object exposes orders, that the orders have a find method that takes an order ID and returns an order, and that the order object has a totals object which has getters and setters for grand totals and discounts. That's a lot of implicit knowledge. But worse, that's a lot of things that cannot change in the future if this code is to continue to work. All the cars in a train are coupled together, as are all the methods and attributes in a train wreck. Let's imagine that the business decides that no order can have a discount of more than 40%. Where would we put the code that enforces that rule? You might say it belongs in the apply discount function we just wrote. That's certainly part of the answer. But with the code the way it is now, you can't know that this is the whole answer. Any piece of code, anywhere, could set fields in the totals object, and if the maintainer of that code didn't get the memo, it wouldn't be checking against the new policy. One way to look at this is to think about responsibilities. Surely the totals object should be responsible for managing the totals. And yet it isn't, it's really just a container for a bunch of fields that anyone can query and update. The fix for that is to apply something we call Tip 45 Tell, Don't Ask. This principle says that you shouldn't make decisions based on the internal state of an object and then update that object. Doing so totally destroys the benefits of encapsulation and, in doing so, spreads the knowledge of the implementation throughout the code. So the first fix for our train wreck is to delegate the discounting to the total object. Public void apply discount, customer, order underscore ID, discount, customer.orders.find, order underscore ID, dot get totals, dot apply discount, discount. We have the same kind of tell don't ask, TDA, issue with the customer object and its orders. We shouldn't fetch its list of orders and search them. We should instead get the order we want directly from the customer. Public void apply discount, customer, order underscore ID, discount, customer.find order, order underscore ID, dot get totals, dot apply discount, discount. The same thing applies to our order object and its totals. Why should the outside world have to know that the implementation of an order uses a separate object to store its totals? Public void apply discount, customer, order underscore ID, discount, customer.find order, order underscore ID, dot apply discount, discount, and this is where we'd probably stop. At this point you might be thinking that TDA would make us add an apply discount to order underscore ID, method to customers. And, if followed slavishly, it would. But TDA is not a law of nature, it's just a pattern to help us recognize problems. In this case, we're comfortable exposing the fact that a customer has orders, and that we can find one of those orders by asking the customer object for it. This is a pragmatic decision. In every application there are certain top-level concepts that are universal. In this application, those concepts include customers and orders. It makes no sense to hide orders totally inside customer objects, they have an existence of their own. So we have no problem creating APIs that expose order objects. The Law of Demeter people often talk about something called the Law of Demeter, or LODE, in relation to coupling. The LODE is a set of guidelines, 37, written in the late 80s by Ian Holland. He created them to help developers on the Demeter project keep their functions cleaner and decoupled. The LODE says that a method defined in a class C should only call other instance methods in C. Its parameters. Methods in objects that it creates, both on the stack and in the heap. Global variables. In the first edition of this book we spent some time describing the LODE. In the intervening 20 years the bloom has faded on that particular rose. We now don't like the global variable clause, for reasons we'll go into in the next section. We also discovered that it's difficult to use this in practice. It's a little like having to parse a legal document whenever you call a method. However, the principle is still sound. We just recommend a somewhat simpler way of expressing almost the same thing. Tip 46: Don't chain method calls. Try not to have more than one dot when you access something. And access something also covers cases where you use intermediate variables, as in the following code. This is pretty poor style. Amount equals customer.orders.last.totals.amount. And so is this. Orders equals customer.orders, last equals orders.last, totals equals last.totals, amount equals totals.amount. There's a big exception to the one dot rule. The rule doesn't apply if the things you're chaining are really unlikely to change. In practice, anything in your application should be considered likely to change. Anything in a third-party library should be considered volatile, particularly if the maintainers of that library are known to change APIs between releases. Libraries that come with the language, however, are probably pretty stable, and so we'd be happy with codes such as people.sort_by, person.age.first, 10.map, person.name. That Ruby code worked when we wrote the first edition, 20 years ago, and will likely still work when we enter the home for old programmers, any day now. Chains and pipelines. In topic 30, transforming programming, we talk about composing functions into pipelines. These pipelines transform data, passing it from one function to the next. This is not the same as a train wreck of method calls, as we are not relying on hidden implementation details. That's not to say that pipelines don't introduce some coupling, they do. The format of the data returned by one function in a pipeline must be compatible with the format accepted by the next. Our experience is that this form of coupling is far less a barrier to changing the code than the form introduced by train wrecks. The evils of globalization. Globally accessible data is an insidious source of coupling between application components. Each piece of global data acts as if every method in your application suddenly gained an additional parameter. After all, that global data is available inside every method. Globals couple code for many reasons. The most obvious is that a change to the implementation of the global potentially affects all the code in the system. In practice, of course, the impact is fairly limited. The problem really comes down to knowing that you've found every place you need to change. Global data also creates coupling when it comes to teasing your code apart. Much has been made of the benefits of code reuse. Our experience has been that reuse should probably not be a primary concern when creating code, but the thinking that goes into making code reusable should be part of your coding routine. When you make code reusable, you give it clean interfaces, decoupling it from the rest of your code. This allows you to extract a method or module without dragging everything else along with it. And if your code uses global data, then it becomes difficult to split it out from the rest. You'll see this problem when you're writing unit tests for code that uses global data. You'll find yourself writing a bunch of setup code to create a global environment just to allow your test to run. Tip 47: Avoid global data. Global data includes singletons. In the previous section we were careful to talk about global data and not global variables. That's because people often tell us, look, no global variables. I wrapped it all as instance data in a singleton object or global module. Try again, Skippy. If all you have is a singleton with a bunch of exported instance variables, then it's still just global data. It just has a longer name. So then folks take this singleton and hide all the data behind methods. Instead of coding config.log_level, they now say config.log_level or config.getLogLevel. This is better because it means that your global data has a bit of intelligence behind it. If you decide to change the representation of log levels, you can maintain compatibility by mapping between the new and old in the config API. But you still have only the one set of configuration data. Global data includes external resources. Any mutable external resource is global data. If your application uses a database, data store, file system, service API, and so on, it risks falling into the globalization trap. Again, the solution is to make sure you always wrap these resources behind code that you control. Tip 48: if it's important enough to be global, wrap it in an API. Inheritance adds coupling. The misuse of subclassing, where a class inherits state and behavior from another class, is so important that we discuss it in its own section. Topic 31, Inheritance Tax. Again, it's all about change. Coupled code is hard to change. Alterations in one place can have secondary effects elsewhere in the code, and often in hard-to-find places that only come to light a month later in production. Keeping your code shy, having it only deal with things it directly knows about, will help keep your applications decoupled, and that will make them more amenable to change. Related sections include Topic 8, The Essence of Good Design, Topic 9, DIY, The Evils of Duplication, Topic 10, Orthogonality, Topic 11, Reversibility, Topic 29, Juggling the Real World, Topic 30, Transforming Programming, Topic 31, Inheritance Tax, Topic 32, Configuration, Topic 33, Breaking Temporal Coupling, Topic 34, Shared State is Incorrect State, Topic 35, Actors and Processes, Topic 36, Blackboards. We discussed Tell, Don't Ask in our 2003 software construction article, The Art of Inbugging. 38. Today, we expect more. Computers have to integrate into our world, not the other way around. And our world is messy. Things are constantly happening, stuff gets moved around, we change our minds. And the applications we write somehow have to work out what to do. This section is all about writing these responsive applications. We'll start off with the concept of an event. Events. An event represents the availability of information. It might come from the outside world, a user clicking a button, or a stock quote update. It might be internal, the result of a calculation is ready, a search finishes. It can even be something as trivial as fetching the next element in a list. Whatever the source, if we write applications that respond to events, and adjust what they do based on those events, those applications will work better in the real world. Their users will. Things don't just happen, they are made to happen. John F. Kennedy. Topic 29, Juggling the Real World. In the old days, when your authors still had their boyish good looks, computers were not particularly flexible. We'd typically organize the way we interacted with them based on their limitations. Find them to be more interactive, and the applications themselves will make better use of resources. But how can we write these kinds of applications? Without some kind of strategy, we'll quickly find ourselves confused, and our applications will be a mess of tightly coupled code. Let's look at 4 strategies that help. 1. Finite state machines. 2. The observer pattern. 3. Publish subscribe. 4. Reactive programming and streams. Finite state machines. Dave finds that he writes code using a finite state machine, FSM, just about every week. Quite often, the FSM implementation will be just a couple of lines of code, but those few lines help untangle a whole lot of potential mess. Using an FSM is trivially easy, and yet many developers shy away from them. There seems to be a belief that they are difficult, or that they only apply if you're working with hardware, or that you need to use some hard-to-understand library. None of these are true. The anatomy of a pragmatic FSM. A state machine is basically just a specification of how to handle events. It consists of a set of states, one of which is the current state. For each state, we list the events that are significant to that state. For each of those events, we define the new current state of the system. For example, we may be receiving multipart messages from a WebSocket. The first message is a header. This is followed by any number of data messages, followed by a trailing message. This could be represented as an FSM like this, images events underscore simple underscore FSM.png. We start in the initial state. If we receive a header message, we transition to the reading message state. If we receive anything else while we're in the initial state, the line labeled with an asterisk, we transition to the error state and we're done. While we're in the reading message state, we can accept either data messages, in which case we continue reading in the same state, or we can accept a trailer message, which transitions us to the done state. Anything else causes a transition to the error state. The neat thing about FSMs is that we can express them purely as data. Here's a table representing our message parser. Images event underscore simple underscore FSM underscore table.png. The rows in the table represent the states. To find out what to do when an event occurs, look up the row for the current state, scan along for the column representing the event, the contents of that cell are the new state. The code that handles it is equally simple. Event simple underscore FSM.rb transitions equals 1. Initial, header, reading. Reading, data, reading, trailer, done. The code that implements the transitions between states is on line 10. It indexes the transition table using the current state, and then indexes the transitions for that state using the message type. If there is no matching new state, it sets the state to error. Adding actions a pure FSM, such as the one we were just looking at, is an event stream parser. Its only output is the final state. We can beef it up by adding actions that are triggered on certain transitions. For example, we might need to extract all of the strings in a source file. A string is text between quotes, but a backslash in a string escapes the next character, so ignore backslash quotes backslash is a single string. Here's an FSM that does this. Images event underscore string underscore FSM.png. This time, each transition has two labels. The top one is the event that triggers it, and the bottom one is the action to take as we move between states. We'll express this in a table, as we did last time. However, in this case each entry in the table is a two-element list containing the next state and the name of an action. Event strings underscore FSM.rb transitions equals hash current new state action to take hash. Look_for_string, double quotes equals, in_string, start_new_string, default equals, look_for_string, ignore. In_string, double quotes equals, look_for_string, finish_current_string, / single quote equals, copy_next_char, add_current_to_string, default equals, in_string, add_current_to_string. Copy_next_char, default equals, in_string, add_current_to_string. We've also added the ability to specify a default transition, taken if the event doesn't match any of the other transitions for this state. Now let's look at the code. Event strings_fsm.rb state equals, look_for_string. Result equals. While ch equals stdin.getState, action equals transitions, state, ch, transitions, state, default, case action when, ignore when, start_new_string result equals, when, add_current_to_string result, ch when, finish_current_string puts result.join end. This is similar to the previous example, in that we loop through the events, the characters in the input, triggering transitions. But it does more than the previous code. The result of each transition is both a new state and the name of an action. We use the action name to select the code to run before we go back around the loop. This code is very basic, but it gets the job done. There are many other variants. The transition table could use anonymous functions or function pointers for the actions. You could wrap the code that implements the state machine in a separate class, with its own state, and so on. There's nothing to say that you have to process all the state transitions at the same time. If you're going through the steps to sign up a user on your app, there's likely to be a number of transitions as they enter their details, validate their email, agree to the 107 different legislated warnings that online apps must now give, and so on. Keeping the state in external storage, and using it to drive a state machine, is a great way to handle these kind of workflow requirements. State machines are a start. State machines are underused by developers, and we'd like to encourage you to look for opportunities to apply them. But they don't solve all the problems associated with events. So let's move on to some other ways of looking at the problems of juggling events. The observer pattern. In the observer pattern we have a source of events, called the observable, and a list of clients, the observers, who are interested in those events. An observer registers its interest with the observable, typically by passing a reference to a function to be called. Subsequently, when the event occurs, the observable iterates down its list of observers and calls the function that each passed it. The event is given as a parameter to that call. Here's a simple example in Ruby. The terminator module is used to terminate the application. Before it does so, however, it notifies all its observers that the application is going to exit. 39. They might use this notification to tidy up temporary resources, commit data, and so on. Event observer.rb module terminator callbacks equals def self.register, callback, callbacks, callback end. Def self.exit, exit_status, callbacks.each, callback, callback, exit_status. Exit, exit_status, end. Terminator.register, dash, status, puts callback 1 sees hash, status, terminator.register, dash, status, puts callback 2 sees hash, status. Terminator.exit, 99, $Ruby event observer.rb callback 1 sees 99 callback 2 sees 99. There's not much code involved in creating an observable. You push a function reference onto a list, and then call those functions when the event occurs. This is a good example of when not to use a library. The observer observable pattern has been used for decades, and it has served us well. It is particularly prevalent in user interface systems, where the callbacks are used to inform the application that some interaction has occurred. But the observer pattern has a problem. Because each of the observers has to register with the observable, it introduces coupling. In addition, because in the typical implementation the callbacks are handled inline by the observable, synchronously, it can introduce performance bottlenecks. This is solved by the next strategy: publish-subscribe. Publish-subscribe. Publish-subscribe, pub-sub, generalizes the observer pattern, at the same time solving the problems of coupling and performance. In the pub-sub model, we have publishers and subscribers. These are connected via channels. The channels are implemented in a separate body of code, sometimes a library, sometimes a process, and sometimes a distributed infrastructure. All this implementation detail is hidden from your code. Every channel has a name. Subscribers register interest in one or more of these named channels, and publishers write events to them. Unlike the observer pattern, the communication between the publisher and subscriber is handled outside your code, and is potentially asynchronous. Although you could implement a very basic pub-sub system yourself, you probably don't want to. Most cloud service providers have pub-sub offerings, allowing you to connect applications around the world. Every popular language will have at least one pub-sub library. Pub-sub is a good technology for decoupling the handling of asynchronous events. It allows code to be added and replaced, potentially while the application is running, without altering existing code. The downside is that it can be hard to see what is going on in a system that uses pub-sub heavily. You can't look at a publisher and immediately see which subscribers are involved with a particular message. Compared to the observer pattern, pub-sub is a great example of reducing coupling by abstracting up through a shared interface, the channel. However, it is still basically just a message passing system. Creating systems that respond to combinations of events will need more than this, so let's look at ways we can add a time dimension to event processing. Reactive programming, streams, and events. If you've ever used a spreadsheet, then you'll be familiar with reactive programming. If a cell contains a formula which refers to a second cell, then updating that second cell causes the first to update as well. The values react as the values they use change. There are many frameworks that can help with this kind of data-level reactivity. In the realm of the browser, React and Vue.js are current favorites, but, this being JavaScript, this information will be out of date before this book is even printed. It's clear that events can also be used to trigger reactions in code, but it isn't necessarily easy to plumb them in. That's where streams come in. Streams let us treat events as if they were a collection of data. It's as if we had a list of events, which got longer when new events arrive. The beauty of that is that we can treat streams just like any other collection. We can manipulate, combine, filter, and do all the other data-ish things we know so well. We can even combine event streams and regular collections. And streams can be asynchronous, which means your code gets the opportunity to respond to events as they arrive. The current de facto baseline for reactive event handling is defined on the site http://reactivex.io http://reactivex.io, which defines a language-agnostic set of principles and documents some common implementations. Here we'll use the RxJS library for JavaScript. Our first example takes two streams and zips them together. The result is a new stream where each element contains one item from the first input stream and one item from the other. In this case, the first stream is simply a list of 5 animal names. The second stream is more interesting. It's an interval timer which generates an event every 500 milliseconds. Because the streams are zipped together, a result is only generated when data is available on both, and so our results stream only emits a value every half second. Event rx0index.js import * as observable from rxjs import, log values, from rexcommon-logger.js. Let animals equals observable.of, and, b, cat, dog, elk, let ticker equals observable.interval, 500. Let combined equals observable.zip, animals, ticker. Combined.subscribe, next equals log values, json.stringify, next. This code uses a simple logging function, 40, which adds items to a list in the browser window. Each item is timestamped with the time in milliseconds since the program started to run. Here's what it shows for our code. Images events _rxjs_0.png. Notice the timestamps. We're getting one event from the stream every 500 milliseconds. Each event contains a serial number, created by the interval observable, and the name of the next animal from the list. Watching it live in a browser, the log lines appear at every half second. Event streams are normally populated as events occur, which implies that the observables that populate them can run in parallel. Here's an example that fetches information about users from a remote site. For this we'll use https://request.in https://request.in, a public site that provides an open REST interface. As part of its API, we can fetch data on a particular, fake, user by performing a GET request to user's ID. Our code fetches the users with the IDs 3, 2, and 1. Event rx1 index.js import asterisk as observable from rxjs import, merge map, from rxjs operators import, rjux, from rxjs rjux. Import, log values, from rexcommon logger.js. Let users equals observable.of, 3, 2, 1. Let result equals users.pipe, merge map, user, equals rjux.getjson, https://request.in API users $user. Result.subscribe, resp equals log values, json.stringify, resp data, equals console.error, json.stringify, The internal details of the code are not too important. What's exciting is the result, shown in the following screenshot, images events _3_users.png. Look at the timestamps. The 3 requests, or 3 separate streams, were processed in parallel. The first to come back, for ID 2, took 82 milliseconds, and the next 2 came back 50 and 51 milliseconds later. Streams of events are asynchronous collections in the previous example, our list of user IDs, in the observable. Users was static. But it doesn't have to be. Perhaps we want to collect this information when people log into our site. All we have to do is to generate an observable event containing their user ID when their session is created, and use that observable instead of the static one. We'd then be fetching details about the users as we received these IDs, and presumably storing them somewhere. This is a very powerful abstraction. We no longer need to think about time as being something we have to manage. Event streams unify synchronous and asynchronous processing behind a common, convenient API. Events are ubiquitous. Events are everywhere. Some are obvious, a button click, a timer expiring. Other are less so, someone logging in, a line in a file matching a pattern. But whatever their source, code that's crafted around events can be more responsive and better decoupled than its more linear counterpart. Related sections include Topic 28, Decoupling. Topic 36, Blackboards. Exercises. Exercise 19, Possible answer. In the FSM section we mentioned that you could move the generic state machine implementation into its own class. That class would probably be initialized by passing in a table of transitions and an initial state. Try implementing the string extractor that way. Exercise 20, Possible answer. Which of these technologies, perhaps in combination, would be a good fit for the following situations? If you receive 3 network interface down events within 5 minutes, notify the operations staff. If it is after sunset, and there is motion detected at the bottom of the stairs followed by motion detected at the top of the stairs, turn on the upstairs lights. You want to notify various reporting systems that an order was completed. In order to determine whether a customer qualifies for a car loan, the application needs to send requests to 3 backend services and wait for the responses. Topic 30, Transforming Programming. If you can't describe what you are doing as a process, you don't know what you're doing. W. Edwards Deming, ATA. All programs transform data, converting an input into an output. And yet when we think about design, we rarely we worry about classes and modules, data structures and algorithms, languages and frameworks. We think that this focus on code often misses the point. We need to get back to thinking of programs as being something that transforms inputs into outputs. When we do, many of the details we previously worried about just evaporate. The structure becomes clearer, the error handling more consistent, and the coupling drops way down. To start our investigation, let's take the time machine back to the 1970s and ask a Unix programmer to write us a program that lists the 5 longest files in a directory tree, where longest means having the largest number of lines. You might expect them to reach for an editor and start typing in C. But they wouldn't, because they are thinking about this in terms of what we have, a directory tree, and what we want, a list of files. Then they'd go to a terminal and type something like $find. Type F for zargs WCL, sort n, tail -5. This is a series of transformations. Find. Type F, write a list of all the files, type F, in or below the current directory, dot, to standard output. Zargs WCL, read lines from standard input and arrange for them all to be passed as arguments to the command WCL. The WC program with the L option counts the number of lines in each of its arguments and writes each result as count file name to standard output. Sort n, sort standard input, assuming each line starts with a number, n, writing the result to standard output. Tail -5. Read standard input and write just the last 5 lines to standard output. Run this in our books directory and we get for 70, test_to_build.pml 487, dbc.pml 719, domain_languages.pml 727, dry.pml 9561. Total. That last line is the total number of lines in all the files, not just those shown, because that's what WC does. We can strip it off by requesting one more line from tail, and then ignoring the last line. $find. Type F for zargs WCL, sort n, tail -6, head -5 470, debug.pml 470, test_to_build.pml 487, dbc.pml 719, domain_languages.pml 727, dry.pml. Let's look at this in terms of the data that flows between the individual steps. Our original requirement, top 5 files in terms of lines, becomes a series of transformations, also show in the figure. Directory name, list of files, list with line numbers, sorted list, highest 5 plus total highest 5. It's almost like an industrial assembly line. Feed raw data in one end and the finished product, information, comes out the other. And we like to think about all code this way. Images WC pipeline.png. Figure 1. The find pipeline as a series of transformations. Tip 49. Programming is about code, but programs are about data. Finding transformations. Sometimes the easiest way to find the transformations is to start with the requirement and determine its inputs and outputs. Now you've defined the function representing the overall program. You can then find steps that lead you from input to output. This is a top-down approach. For example, you want to create a website for folks playing word games that finds all the words that can be made from a set of letters. Your input here is a set of letters, and your output is a list of 3-letter words, 4-letter words, and so on. LVing is transformed to 3 equals ivy, lin, nil, yin. 4 equals inly, liney, viney. 5 equals vinyl. Yes, they are all words, at least according to the macOS dictionary. The trick behind the overall application is simple. We have a dictionary which groups words by a signature, chosen so that all words containing the same letters will have the same signature. The simplest signature function is just the sorted list of letters in the word. We can then look up an input string by generating a signature for it, and then seeing which words, if any, in the dictionary have that same signature. Thus the anagram finder breaks down into 4 separate transformations. STEP. Transformation sample data. Step 0. Initial input ILVing. Step 1. All combinations of 3 or more letters. VIN, VI, VIL, VNY, VNL, VYL, INI, INL, IL, NYL, VINI, VINL, VIL, VNYL, INIL, VINL. Step 2. Signatures of the combinations. INV, IV, ILV, NVY, LNV, LVY, INI, ILN, ILI, LNY, INV, ILNV, ILV, LNVY, ILNI, ILNV. Step 3. List of all dictionary words which match any of the signatures. Ivy, yin, nil, lin, viney, liney, inly, vinyl. Step 4. Words grouped by length 3 equals ivy, lin, nil, yin. 4 equals inly, liney, viney. 5 equals vinyl. Transformations all the way down. Let's start by looking at step 1, which takes a word and creates a list of all combinations of 3 or more letters. This step can itself be expressed as a list of transformations. Step transformation sample data. Step 1.0. Initial input vinyl. Step 1.1. Convert to characters. V-I-N-Y-L. Step 1.2. Get all subsets, V-I. V-I, V-N, V-Y. V-I-N, V-I-Y. V-N-Y-L, I-N-Y-L, V-I-N-Y-L. Step 1.3. Only those longer than 3 characters, V-I-N, V-I-Y. I-N-Y-L, V-I-N-Y-L. Step 1.4. Convert back to strings, VIN, VI, INIL, vinyl. We've now reached the point where we can easily implement each transformation in code, using Elixir in this case. Function pipelines anagrams lib anagrams.x. Def all underscore subsets underscore longer underscore than underscore 3 underscore characters, word, do word, string dot code points, comb dot subsets, stream dot filter, fn subset dash length, subset, equals 3 end, stream dot map, and list dot to underscore string, and 1, end what's with the operator. Elixir, along with many other functional languages, has a pipeline operator, sometimes called a forward pipe or just a pipe. 41. All it does is take the value on its left and insert it as the first parameter of the function on its right, so vinyl, string dot code points, comb dot subsets is the same as writing comb dot subsets, string dot code points, vinyl. Other languages may inject this piped value as the last parameter of the next function. It largely depends on the style of the built-in libraries. You might think that this is just syntactic sugar. But in a very real way, the pipeline operator is a revolutionary opportunity to think differently. Using a pipeline means that you're automatically thinking in terms of transforming data. Each time you see, you're actually seeing a place where data is flowing between one transformation and the next. Many languages have something similar. Elm, F#, and Swift have. Clojure has dash and dash, which work a little differently. A has %. Haskell both has pipe operators and makes it easy to declare new ones. As we write this, there's talk of adding to JavaScript. If your current language supports something similar, you're in luck. If it doesn't, C language X doesn't have pipelines. Anyway, back to the code. Keep on transforming. Now look at step 2 of the main program, where we convert the subsets into signatures. Again, it's a simple transformation. A list of subsets becomes a list of signatures. Step transformation sample data. Step 2.0. Initial input VIN, VI, INIL, vinyl. Step 2.1. Convert to signatures. INV, IV, ILNI, INLV. The Elixir code in the following listing is just as simple. Function pipelines anagrams lib anagrams.xdef as underscore unique underscore signatures, subsets, do subsets, stream.map, and dictionary.signature underscore of one. And now we transform that list of signatures. Each signature gets mapped to the list of known words with the same signature, or nil if there are no such words. We then have to remove the nils and flatten the nested lists into a single level. Function pipelines anagrams lib anagrams.xdef find underscore in underscore dictionary, signatures, do signatures, stream.map, and dictionary.lookup underscore by underscore signature 1. Stream.reject, and is underscore nil 1, stream.concat, and 1, end step 4, grouping the words by length, is another simple transformation, converting our list into a map where the keys are the lengths, and the values are all words with that length. Function pipelines anagrams lib anagrams.xdef group underscore by underscore length, words, do words, enum.sort, enum.group underscore by, and string.length 1, end. Putting it all together, we've written each of the individual transformations. Now it's time to string them all together into our main function. Function pipelines anagrams lib anagrams.x. Def anagrams underscore in, word, do. Word, all underscore subsets underscore longer underscore than underscore 3 underscore characters, as underscore unique underscore signatures, find underscore in underscore dictionary, group underscore by underscore length, and does it work? Let's try it. IX, 1, anagrams underscore in living percent, 3 equals, ivy, lin, nil, yin. 4 equals, inly, liney, viney, 5 equals, vinyl. Language X doesn't have pipelines. Pipelines have been around for a long time, but only in niche languages. They've only moved into the mainstream recently, and many popular languages still don't support the concept. The good news is that thinking in transformations doesn't require a particular language syntax, it's more a philosophy of design. You still construct your code as transformations, but you write them as a series of assignments. Const content equals file.read, file underscore name, const lines equals find underscore matching underscore lines, content, pattern, const result equals truncate underscore lines, lines. It's a little more tedious, but it gets the job done. Why is this so great? Let's look at the body of the main function again. Word, all underscore subsets underscore longer underscore than underscore 3 underscore characters, as underscore unique underscore signatures, find underscore in underscore dictionary, group underscore by underscore length. It's simply a chain of the transformations needed to meet our requirement, each taking input from the previous transformation and passing output to the next. That comes about as close to literate code as you can get. But there's something deeper, too. If your background is object-oriented programming, then your reflexes demand that you hide data, encapsulating it inside objects. These objects then chatter back and forth, changing each other's state. This introduces a lot of coupling, and it is a big reason that OO systems can be hard to change. Tip 50: don't hoard state, pass it around. In the transformational model, we turn that on its head. Instead of little pools of data spread all over the system, think of data as a mighty river, a flow. Data becomes a peer-to functionality. A pipeline is a sequence of code data. The data is no longer tied to a particular group of functions, as it is in a class definition. Instead, it is free to represent the unfolding progress of our application as it transforms its inputs into its outputs. This means that we can greatly reduce coupling. In topic 15, estimating, we talked about estimating things such as how long it takes to walk across town, or how long a project will take to finish. However, there is another kind of estimating that pragmatic programmers use almost daily, estimating the resources that algorithms use: time, processor, memory, and so on. This kind of estimating is often crucial. Given a choice between two ways of doing something, which do you pick? You know how long your program runs with 1,000 records, but how will it scale to 1 million? What parts of the code need optimizing? It turns out that these questions can often be answered using common sense, some analysis, and a way of writing approximations called the Big O notation. What do we mean by estimating algorithms? Most non-trivial algorithms handle some kind of variable input, sorting strings, inverting a matrix, or decrypting a message with an bit key. Normally, the size of this input will affect the algorithm. The larger the input, the longer the running time or the more memory used. If the relationship were always linear, so that the time increased in direct proportion to the value of, this section wouldn't be important. However, most significant algorithms are not linear. The good news is that many are sublinear. A binary search, for example, doesn't need to look at every candidate when finding a Topic 39 Algorithm speed. Match. The bad news is that other algorithms are considerably worse than linear. Runtimes or memory requirements increase far faster than. An algorithm that takes a minute to process 10 items may take a lifetime to process 100. We find that whenever we write anything containing loops or recursive calls, we subconsciously check the runtime and memory requirements. This is rarely a formal process, but rather a quick confirmation that what we're doing is sensible in the circumstances. However, we sometimes do find ourselves performing a more detailed analysis. That's when Big O notation comes in handy. Big O notation. The Big O notation, written, is a mathematical way of dealing with approximations. When we write that a particular sort routine sorts records in time, we are simply saying that the worst-case time taken will vary as the square of double the number of records, and the time will increase roughly fourfold. Think of the as meaning on the order of. The notation puts an upper bound on the value of the thing we're measuring, time, memory, and so on. If we say a function takes time, then we know that the upper bound of the time it takes will not grow faster than. Sometimes we come up with fairly complex functions, but because the highest order term will dominate the value as increases, the convention is to remove all low order terms, and not to bother showing any constant multiplying factors. This is actually a feature of the notation. One algorithm may be 1,000 times faster than another algorithm, but you won't know it from the notation. Big O is never going to give you actual numbers for time or memory or whatever. It simply tells you how these values will change as the input changes. Figure 3, runtimes of various algorithms shows several common notations you'll come across, along with a graph comparing running times of algorithms in each category. Clearly, things quickly start getting out of hand once we get over have on your running time or memory consumption. Tip 63. Estimate the order of your algorithms. There are some approaches you can take to address potential problems. If you have an algorithm that is, try to find a divide and conquer approach that will take you down to. If you're not sure how long your code will take, or how much memory it will use, try running it, varying the input record count or whatever is likely to impact the runtime. Then plot the results. You should soon get a good idea of the shape of the curve. Is it curving upward, a straight line, or flattening off as the input size increases? 3 or 4 points should give you an idea. Also consider just what you're doing in the code itself. A simple loop may well perform better than a complex one for smaller values of, particularly if the algorithm has an expensive inner loop. In the middle of all this theory, don't forget that there are practical considerations as well. Runtime may look like it increases linearly for small input sets. But feed the code millions of records and suddenly the time degrades as the system starts to thrash. If you test a sort routine with random input keys, you may be surprised the first time it encounters ordered input. Try to cover both the theoretical and practical bases. After all this estimating, the only timing that counts is the speed of your code, running in the production environment, with real data. This leads to our next tip. Tip 64. Test your estimates. If it's tricky getting accurate timings, use code profilers to count the number of times the different steps in your algorithm get executed, and plot these figures against the size of the input. Best isn't always best. You also need to be pragmatic about choosing appropriate algorithms. The fastest one is not always the best for the job. Given a small input set, a straightforward insertion sort will perform just as well as a quicksort, and will take you less time to write and debug. You also need to be careful if the algorithm you choose has a high setup cost. For small input sets, this setup may dwarf the running time and make the algorithm inappropriate. Also be wary of premature optimization. It's always a good idea to make sure an algorithm really is a bottleneck before investing your precious time trying to improve it. Related sections include Topic 15. Estimating. Challenges. Every developer should have a feel for how algorithms are designed and analyzed. Robert Sedgwick has written a series of accessible books on the subject, Algorithms, SW11, and Introduction to the Analysis of Algorithms, SF13, and others. We recommend adding one of his books to your collection, and making a point of reading it. For those who like more detail than Sedgwick provides, read Donald Knuth's definitive Art of Computer Programming books, which analyze a wide range of algorithms. The Art of Computer Programming, Volume 1. Fundamental Algorithms, New 98. The Art of Computer Programming, Volume 2, Semi-Numerical Algorithms, New 98A. The Art of Computer Programming, Volume 3, Sorting and Searching, New 98B. The Art of Computer Programming, Volume 4A, Combinatorial Algorithms, Part 1, New 11. In the first exercise that follows we look at sorting arrays of long integers. What is the impact if the keys are more complex, and the overhead of key comparison is high? Does the key structure affect the efficiency of the sort algorithms, or is the fastest sort always fastest? Exercises. Exercise 28, Possible Answer. We coded a set of simple sort routines, 54, in Rust. Run them on various machines available to you. Do your figures follow the expected curves? What can you deduce about the relative speeds of your machines? What are the effects of various compiler optimization settings? Exercise 29, Possible Answer. In common sense estimation, we claimed that a binary chop is. Can you prove this? Exercise 30, Possible Answer. In Figure 3, runtimes of various algorithms, we claimed that is the same as, or indeed logarithms to any base. Can you explain why? Unfortunately, the most common metaphor for software development is building construction. Bertrand Meyer's classic work Object-Oriented Software Construction, May 97, uses the term software construction, and even your humble authors edited the software construction column for IEEE software in the early 2000s, 55. But using construction as the guiding metaphor implies the following steps. 1. An architect draws up blueprints. 2. Contractors dig the foundation, build the superstructure, wire and plumb, and apply finishing touches. 3. The tenants move in and live happily ever after, calling building maintenance to fix any problems. Well, software doesn't quite work that way. Rather than construction, software is more like gardening. It is more organic than concrete. You plant many things in a garden according to an initial plan and conditions. Some thrive, others are destined to end up as compost. You may move plantings. Topic 40 Refactoring. As a program evolves, it will become necessary to rethink earlier decisions and rework portions of the code. This process is perfectly natural. Code needs to evolve, it's not a static thing. Change and decay in all around I see. HF, light abide with me. Relative to each other to take advantage of the interplay of light and shadow, wind and rain. Overgrown plants get split or pruned, and colors that clash may get moved to more aesthetically pleasing locations. You pull weeds, and you fertilize plantings that are in need of some extra help. You constantly monitor the health of the garden, and make adjustments to the soil, the plants, the layout, as needed. Business people are comfortable with the metaphor of building construction. It is more scientific than gardening, it's repeatable, there's a rigid reporting hierarchy for management, and so on. But we're not building skyscrapers, we aren't as constrained by the boundaries of physics and the real world. The gardening metaphor is much closer to the realities of software development. Perhaps a certain routine has grown too large, or is trying to accomplish too much. It needs to be split into two. Things that don't work out as planned need to be weeded or pruned. Rewriting, reworking, and re-architecting code is collectively known as restructuring. But there's a subset of that activity that has become practiced as refactoring. Refactoring, FAU 19, is defined by Martin Fowler as a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. The critical parts of this definition are that 1. The activity is disciplined, not a free-for-all. 2. External behavior does not change, this is not the time to add features. Refactoring is not intended to be a special, high-ceremony, once-in-a-while activity, like plowing under the whole garden in order to replant. Instead, refactoring is a day-to-day activity, taking low-risk small steps, more like weeding and raking. Instead of a free-for-all, wholesale rewrite of the codebase, it's a targeted, precision approach to help keep the code easy to change. In order to guarantee that the external behavior hasn't changed, you need good, automated unit testing that validates the behavior of the code. When should you refactor? You refactor when you've learned something, when you understand something better than you did last year, yesterday, or even just 10 minutes ago. Perhaps you've come across a stumbling block because the code doesn't quite fit anymore, or you notice two things that should really be merged, or anything else at all strikes you as being wrong. Don't hesitate to change it. There's no time like the present. Any number of things may cause code to qualify for refactoring. Duplication. You've discovered a violation of the DRY principle. Non-orthogonal design. You've discovered something that could be made more orthogonal. Outdated knowledge. Things change, requirements drift, and your knowledge of the problem increases. Code needs to keep up. Usage. As the system gets used by real people under real circumstances, you realize some features are now more important than previously thought, and must-have features perhaps weren't. Performance. You need to move functionality from one area of the system to another to improve performance. The tests pass. Yes. Seriously. We did say that refactoring should be a small-scale activity, backed up by good tests. So when you've added a small amount of code, and that one extra test passes, you now have a great opportunity to dive in and tidy up what you just wrote. Refactoring your code, moving functionality around and updating. Security basic principles. Pragmatic programmers have a healthy amount of paranoia. We know we have faults and limitations, and that external attackers will seize on any opening we leave to compromise our systems. Your particular development and deployment environments will have their own security-centric needs, but there are a handful of basic principles that you should always bear in mind. 1. Minimize attack surface area. 2. Principle of least privilege. 3. Secure defaults. 4. Encrypt sensitive data. 5. Maintain security updates. Let's take a look at each of these. Minimize attack surface area. The attack surface area of a system is the sum of all access points where an attacker can enter data, extract data, or invoke execution of a service. Here are a few examples. Code complexity leads to attack vectors. Code complexity makes the attack surface larger, with more opportunities for unanticipated side effects. Think of complex code as making the surface area more porous and open to infection. Once again, simple, smaller code is better. Less code means fewer bugs, fewer opportunities for a crippling security hole. Simpler, tighter, less complex code is easier to reason about, easier to spot potential weaknesses. Input data is an attack vector. Never trust data from an external entity. Always sanitize it before passing it onto a database, view rendering, or other processing. 63. Some languages can help with this. In Ruby, for example, variables holding external input are tainted, which limits what operations can be performed on them. For example, this code apparently uses the WC utility to report on the number of characters in a file whose name is supplied at runtime. Safety taint.rb. Puts enter a file name to count. Name equals get system, WCC shop, name. A nefarious user could do damage like this. Enter a file name to count, test.that, or mrf. However, setting the safe level to 1 will taint external data, which means it can't be used in dangerous contexts. Safety taint.rb. $safe equals 1. Puts enter a file name to count, name equals get system, WCC shop, name, ~~~ session $ruby taint.rb. Enter a file name to count, test.that, or mrf. Code safety taint.rb. 5. In system, insecure operation, system, security error, from code safety taint.rb. 5. In main ~~~. Unauthenticated services are an attack vector by their very nature. Any user anywhere in the world can call unauthenticated services, so barring any other handling or limiting, you've immediately created an opportunity for a denial of service attack at the very least. Quite a few of highly public data breaches recently were caused by developers accidentally putting data in unauthenticated, publicly readable data stores in the cloud. Authenticated services are an attack vector. Keep the number of authorized users at an absolute minimum. Cull unused, old, or outdated users and services. Many net-enabled devices have been found to contain simple default passwords or unused, unprotected administrative accounts. If an account with deployment credentials is compromised, your entire product is compromised. Output data is an attack vector. There's a, possibly apocryphal, story about a system that dutifully reported the error message password is used by another user. Don't give away information. Make sure that the data you report is appropriate for the authorization of that user. Truncate or obfuscate potentially risky information such as social security or other government ID numbers. Debugging info is an attack vector. There's nothing as heartwarming as seeing a full stack trace with data on your local ATM machine, an airport kiosk, or crashing web page. Information designed to make debugging easier can make breaking in easier as well. Make sure any test window, discussed here, and runtime exception reporting is protected from spying eyes. 64. Tip 72. Keep it simple and minimize attack surfaces. Principle of least privilege. Another key principle is to use the least amount of privilege for the shortest time you can get away with. In other words, don't automatically grab the highest permission level, such as root or administrator. If that high level is needed, take it, do the minimum amount of work, and relinquish your permission quickly to reduce the risk. This principle dates back to the early 1970s. Every program and every privileged user of the system should operate using the least amount of privilege necessary to complete the job. Jerome Saltzer, Communications of the ACM, 1974. Take the login program on Unix-derived systems. It initially executes with root privileges. As soon as it finishes authenticating the correct user, though, it drops the high-level privilege to that of the user. This doesn't just apply to operating system privilege levels. Does your application implement different levels of access? Is it a blunt tool, such as administrator versus user? If so, consider something more finely grained, where your sensitive resources are partitioned into different categories, and individual users have permissions for only certain of those categories. This technique follows the same sort of idea as minimizing surface area, reducing the scope of attack vectors, both by time and by privilege level. In this case, less is indeed more. Secure defaults. The default settings on your app, or for your users on your site, should be the most secure values. These might not be the most user-friendly or convenient values, but it's better to let each individual decide for themselves the trade-offs between security and convenience. For example, the default for password entry might be to hide the password as entered, replacing each character with an asterisk. If you're entering a password in a crowded public place, or projected before a large audience, that's a sensible default. But some users might want to see the password spelled out, perhaps for accessibility. If there's little risk someone is looking over their shoulder, that's a reasonable choice for them. Encrypt sensitive data. Don't leave personally identifiable information, financial data, passwords, or other credentials in plain text, whether in a database or some other external file. If the data gets exposed, encryption offers an additional level of safety. In Topic 19, Version control. We strongly recommend putting everything needed for the project under version control. Well, almost everything. Here's one major exception to that rule. Don't check in secrets, API keys, SSH keys, encryption passwords or other credentials alongside your source code in version control. Keys and secrets need to be managed separately, generally via config files or environment variables as part of build and deployment. Do not provide password hints to unauthenticated users, or prompt for specific types of information, example, what was the name of your first pet? Do not disable the paste function in the browser. Crippling the functionality of the browser and password managers does not make your system more secure. In fact, it drives users to create simpler, shorter passwords that are much easier to compromise. Both the NIST in the US and the National Cyber Security Centre in the UK specifically require verifiers to allow paste functionality for this reason. Do not impose other composition rules. For example, do not mandate any particular mix of upper and lower case, numerics, or special characters, or prohibit repeating characters, and so on. Do not arbitrarily require users to change their passwords after some length of time. Only do this for a valid reason, example, if there has been a breach. You want to encourage long, random passwords with a high degree of entropy. Putting artificial constraints limits entropy and encourages bad password habits, leaving your users' accounts vulnerable to takeover. Maintain security updates. Updating computer systems can be a huge pain. You need that security patch, but as a side effect it breaks some portion of your application. You could decide to wait, and defer the update until password antipatterns. One of the fundamental problems with security is that oftentimes good security runs counter to common sense or common practice. For example, You might think that strict password requirements would increase security for your application or site. You'd be wrong. Strict password policies will actually lower your security. Here's a short list of very bad ideas, along with some recommendations from the NIST. Do not restrict password length to less than 64 characters. NIST recommends 256 as a good maximum length. Do not truncate the user's chosen password. Do not restrict special characters such as $hash or. See the note about Bobby tables earlier in this section. If special characters in your password will compromise your system, you have bigger problems. The NIST says to accept all printing ASCII characters, space, and Unicode. 65. Later. That's a terrible idea, because now your system is vulnerable to a known exploit. Tip 73. Apply security patches quickly. This tip affects every net-connected device, including phones, cars, appliances, personal laptops, developer machines, build machines, production servers, and cloud images. Everything. And if you think that this doesn't really matter, just remember that the largest data breaches in history, so far, were caused by systems that were behind on their updates. Don't let it happen to you. Common sense versus crypto. It's important to keep in mind that common sense may fail you when it comes to matters of cryptography. The first and most important rule when it comes to crypto is never do it yourself. 66. Even for something as simple as passwords, common practices are wrong-headed. See the sidebar password anti-patterns. Once you get into the world of crypto, even the tiniest, most insignificant-looking error can compromise everything. Your clever new, homemade encryption algorithm can probably be broken by an expert in minutes. You don't want to do encryption yourself. As we've said elsewhere, rely only on reliable things, well-vetted, thoroughly examined, well-maintained, frequently updated, preferably open-source libraries and frameworks. Beyond simple encryption tasks, take a hard look at other security-related features of your site or application. Take authentication, for instance. In order to implement your own login with password or biometric authentication, you need to understand how hashes and salts work, how crackers use things like rainbow tables, why you shouldn't use MD5 or SHA-1, and a host of other concerns. And even if you get all that right, at the end of the day you're still responsible for holding on to the data and keeping it secure, subject to whatever new legislation and legal obligations come up. Or, you could take the pragmatic approach and let someone else worry about it and use a third-party authentication provider. This may be an off-the-shelf service you run in-house, or it could be a third party in the cloud. Authentication services are often available from email, phone, or social media providers, which may or may not be appropriate for your application. In any case, these folks spend all their days keeping their systems secure, and they're better at it than you are. Stay safe out there. Related sections include Topic 23, Design by Contract. Topic 24, Dead programs tell no lies. Topic 25, Assertive Programming. Topic 38, Programming by Coincidence. Topic 45, The Requirements Pit. They reveal a lot about your intent and belief. We believe that things should be named according to the role they play in your code. This means that, whenever you create something, you need to pause and think, what is my motivation to create this? This is a powerful question, because it takes you out of the immediate problem-solving mindset and makes you look at the bigger picture. When you consider the role of a variable or function, you're thinking about what is special about it, about what it can do, and what it interacts with. Often, we find ourselves realizing that what we were about to do made no sense, all because we couldn't come up with an appropriate name. There's some science behind the idea that names are deeply meaningful. It turns out that the brain can read and understand. The beginning of wisdom is to call things by their proper name. Confucius. Topic 44, Naming things. What's in a name? When we're programming, the answer is everything. We create names for applications, subsystems, modules, functions, variables. We're constantly creating new things and bestowing names on them. And those names are very, very important, because words really fast, faster than many other activities. This means that words have a certain priority when we try to make sense of something. This can be demonstrated using the Stroop effect, 67. Look at the following panel. It has a list of color names or shades, and each is shown in a color or shade. But the names and colors don't necessarily match. Here's part 1 of the challenge. Say aloud the name of each color as written. Sad smiley 68, images stroop_color.png. Now repeat this, but instead say aloud the color used to draw the word. Harder, A. It's easy to be fluent when reading, but way harder when trying to recognize colors. Your brain treats written words as something to be respected. We need to make sure the names we use live up to this. Let's look at a couple of examples. We're authenticating people who access our site that sells jewelry made from old graphics cards. Let user equals authenticate, credentials. The variable is user because it's always user. But why? It means nothing. How about customer, or buyer? That way we get constant reminders as we code of what this person is trying to do, and what that means to us. We have an instance method that discounts an order, public void deduct %, double amount, // Two things here. First, deduct % is what it does and not why it does it. Then the name of the parameter amount is at best misleading. Is it an absolute amount, a percentage? Perhaps this would be better. Public void apply discount, percentage discount, // The method name now makes its intent clear. We've also changed the parameter from a double to a percentage, a type we've defined. We don't know about you, but when dealing with percentages we never know if the value is supposed to be between 0 and 100 or 0.0 and 1.0. Using a type documents what the function expects. We have a module that does interesting things with Fibonacci numbers. One of those things is to calculate the number in the sequence. Stop and think what you'd call this function. Most people we ask would call it fib. Seems reasonable, but remember it will normally be called in the context of its module, so the call would be fib.fib_n. How about calling it of or nth instead? Fib.of, 0, #= 0 fib.nth, 20, #= 4181. When naming things, you're constantly looking for ways of clarifying what you mean, and that act of clarification will lead you to a better understanding of your code as you write it. However, not all names have to be candidates for a literary prize. Honor the culture. Most introductory computer texts will admonish you never to use single-letter variables such as I, J, or K. 69, we think they're wrong. Sort of. In fact, it depends on the culture of that particular programming language or environment. In the C programming language, I, J, and K are traditionally used as loop increment variables, S is used for a character string, and so on. If you program in that environment, that's what you are used to seeing, and it would be jarring, and hence wrong, to violate that norm. On the other hand, using that convention in a different environment where it's not expected is just as wrong. You'd never do something heinous like this closure example, which assigns a string to variable I, let, I hello world, println I. Some language communities prefer camel case, with embedded capital letters, while others prefer snake underscore case with embedded underscores to separate words. The languages themselves will of course accept either, but that doesn't make it right. Honor the local culture. The exception that proves the rule while we strive for clarity in code, branding is a different matter entirely. There's a well-established tradition that projects and project teams should have obscure, clever names. Names of Pokemon, Marvel superheroes, cute mammals, Lord of the Rings characters, you name it. Literally. Some languages allow a subset of Unicode in names. Get a sense of what the community expects before going all cute with names like SN or consistency. Emerson is famous for writing a foolish consistency is the hobgoblin of little minds, but Emerson wasn't on a team of programmers. Every project has its own vocabulary, jargon, words that have a special meaning to the team. Order means one thing to a team creating an online store, and something very different to a team whose app charts the lineage of religious groups. It's important that everyone on the team knows what these words mean, and that they use them consistently. One way is to encourage a lot of communication. If everyone pair programs, and pairs switch frequently, then jargon will spread asthmatically. Another way is to have a project glossary, listing the terms that have special meaning to the team. This is an informal document, possibly maintained on a wiki, possibly just index cards on a wall somewhere. After a while, the project jargon will take on a life of its own. As everyone gets comfortable with the vocabulary, you'll be able to use the jargon as a shorthand, expressing a lot of meaning accurately and concisely. This is exactly what a pattern language is. Renaming is even harder. No matter how much effort you put in up front, things change. Code is refactored, usage shifts, meaning becomes subtly altered. If you aren't vigilant about updating names as you go, you can quickly descend into a nightmare much worse than meaningless names, misleading names. Have you ever had someone explain inconsistencies in code such as, the routine called getData really writes data to an archive file? As we discuss in Topic 3, Software Entropy, when you spot a problem, fix it right here and now. When you see a name that no longer expresses the intent, or is misleading or confusing, fix it. You've got 4 regression tests, so you'll spot any instances you may have missed. Tip 74: Name well, rename when needed. If for some reason you can't change the now wrong name, then you've got a bigger problem, an etc. violation. See Topic 8, The Essence of Good Design. Fix that first, then change the offending name. Make renaming easy, and do it often. Otherwise you'll have to explain to the new folks on the team that getData really writes data to a file, and you'll have to do it with a straight face. Related sections include Topic 3, Software Entropy. Topic 40, Refactoring. Topic 45, The Requirements Pit. Challenges. When you find a function or method with an overly generic name, try and rename it to express all the things it really does. Now it's an easier target for refactoring. In our examples, we suggested using more specific names such as buyer instead of the more traditional and generic user. What other names do you habitually use that could be better? Are the names in your system congruent with user terms from the domain? If not, why? Does this cause a Stroop effect style cognitive dissonance for the team? Are names in your system hard to change? What can you do to fix that particular broken window? Chapter 8. Before the project. At the very beginning of a project, you and the team need to learn the requirements. Simply being told what to do or listening to users is not enough. Read Topic 45, The Requirements Pit, and learn how to avoid the common traps and pitfalls. Conventional wisdom and constraint management are the topics of Topic 46, Solving Impossible Puzzles. Whether you are performing requirements, analysis, coding, or testing, difficult problems will crop up. Most of the time, they won't be as difficult as they first appear to be. And when that impossible project comes up, we like to turn to our secret weapon, Topic 47, Working Together. And by working together we don't mean sharing a massive requirements document, flinging heavily CC'd emails or enduring endless meetings. We mean solving problems together while coding. We'll show you who you need and how to start. Even though the Agile Manifesto begins with individuals and interactions over processes and tools, virtually all Agile projects begin with an ironic discussion of which process and which tools they'll use. But no matter how well thought out it is, and regardless of which best practices it includes, no method can replace thinking. You don't need any particular process or tool. What you do need is the Topic 48, the essence of agility. With these critical issues sorted out before the project gets underway, you can be better positioned to avoid analysis paralysis and actually begin and complete your successful project. Topic 45: The Requirements Pit. Perfection is achieved, not when there is nothing left to add but when there is nothing left to take away. Antoine de Saint-Exupéry, Wind, Sand and Stars, 1939. Many books and tutorials refer to requirements gathering as an early phase of the project. The word gathering seems to imply a tribe of happy analysts, foraging for nuggets of wisdom that are lying on the ground all around them while the pastoral symphony plays gently in the background. Gathering implies that the requirements are already there, you need merely find them, place them in your basket, and be merrily on your way. It doesn't quite work that way. Requirements rarely lie on the surface. Normally, they are buried deep beneath layers of assumptions, misconceptions, and politics. Even worse, often they don't really exist at all. Tip 75: No one knows exactly what they want. The requirements myth. In the early days of software, computers were more valuable, in terms of amortized cost per hour, than the people who worked with them. We saved money by trying to get things correct the first time. Part of that process was trying to specify exactly what we were going to get the machine to do. We'd start by getting a specification of the requirements, parley that into a design document, then into flowcharts and pseudocode, and finally into code. Before feeding it into a computer, though, we'd spend time desk checking it. It cost a lot of money. And that cost meant that people only tried to automate something when they knew exactly what they wanted. As early machines were fairly limited, the scope of problems they solved was constrained. It was actually possible to understand the whole problem before you started. But that is not the real world. The real world is messy, conflicted, and unknown. In that world, exact specifications of anything are rare, if not downright impossible. That's where we programmers come in. Our job is to help people understand what they want. In fact, that's probably our most valuable attribute. And it's worth repeating. Tip 76: Programmers help people understand what they want. Programming as therapy. Let's call the people who ask us to write software our clients. The typical client comes to us with a need. The need may be strategic, but it is just as likely to be a tactical issue, a response to a current problem. The need may be for a change to an existing system, or it may ask for something new. The need will sometimes be expressed in business terms, and sometimes in technical ones. The mistake new developers often make is to take this statement of need and implement a solution for it. In our experience, this initial statement of need is not an absolute requirement. The client may not realize this, but it is really an invitation to explore. Let's take a simple example. You work for a publisher of paper and electronic books. You're given a new requirement. Shipping should be free on all orders costing $50 or more. Stop for a second and imagine yourself in that position. What's the first thing that comes to mind? The chances are very good that you had questions. Does the $50 include tax? Does the $50 include current shipping charges? Does the $50 have to be for paper books, or can the order also include ebooks? What kind of shipping is offered? Priority? Ground? What about international orders? How often will the $50 limit change in the future? That's what we do. When given something that seems simple, we annoy people by looking for edge cases and asking about them. The chances are the client will have already thought of some of these, and just assumed that the implementation would work that way. Asking the question just flushes that information out. But other questions will likely be things that the client hadn't previously considered. That's where things get interesting, and where a good developer learns to be diplomatic. We were wondering about the $50 total. Does that include what we'd normally charge for shipping? Client, of course. It's the total they'd pay us. You, that's nice and simple for our customers to understand. I can see the attraction. But I can see some less scrupulous customers trying to game that system. Client, how so? You, well, let's say they buy a book for $25, and then select overnight shipping, the most expensive option. That'll likely be about $30, making the whole order $55. We'd then make the shipping free, and they'd get overnight shipping on a $25 book for just $25. At this point the experienced developer stops. Deliver facts, and let the client make the decisions. Client, ouch. That certainly wasn't what I intended, we'd lose money on those orders. What are the options? And this starts an exploration. Your role in this is to interpret what the client says and to feed back to them the implications. This is both an intellectual process and a creative one. You're thinking on your feet and you're contributing to a solution that is likely to be better than one that either you or the client would have produced alone. Requirements are a process. In the previous example, the developer took the requirements and fed back a consequence to the client. This initiated the exploration. During that exploration, you are likely to come up with more feedback as the client plays with different solutions. This is the reality of all requirements gathering. Tip 77. Requirements are learned in a feedback loop. Your job is to help the client understand the consequences of their stated requirements. You do that by generating feedback, and letting them use that feedback to refine their thinking. In the previous example, the feedback was easy to express in words. Sometimes that's not the case. And sometimes you honestly won't know enough about the domain to be as specific as that. In those cases, pragmatic programmers rely on the "is this what you meant" school of feedback. We produce mock-ups and prototypes, and let the client play with them. Ideally, the things we produce are flexible enough that we can change them during our discussions with the client, letting us respond to "that isn't what I meant" with "so more like this." Sometimes these mock-ups can be thrown together in an hour or so. They are obviously just hacks to get an idea across. But the reality is that all of the work we do is actually some form of mock-up. Even at the end of a project, we're still interpreting what our client wants. In fact, by that point we're likely to have more clients, the QA people, operations, marketing, and maybe even test groups of customers. So the pragmatic programmer looks at all of the project as a requirements gathering exercise. That's why we prefer short iterations, ones that end with direct client feedback. This keeps us on track, and makes sure that if we do go in the wrong direction, the amount of time lost is minimized. Walk in your client's shoes. There's a simple technique for getting inside your client's heads that isn't used often enough. Become a client. Are you writing a system for the help desk? Spend a couple of days monitoring the phones with an experienced support person. Are you automating a manual stock control system? Work in the warehouse for a week, 70. As well as giving you insight into how the system will really be used, you'd be amazed at how the request "may I sit in for a week while you do your job" helps build trust and establishes a basis for communication with your clients. Just remember not to get in the way. Tip 78. Work with a user to think like a user. Gathering feedback is also the time to start to build a rapport with your client base, learning their expectations and hopes for the system you are building. See topic 52, Delight your users, for more. Requirements versus policy. Let's imagine that while discussing a human resources system, a client says only an employee's supervisors and the personnel department may view that employee's records. Is this statement truly a requirement? Perhaps today, but it embeds business policy in an absolute statement. Business policy? Requirement? It's a relatively subtle distinction, but it's one that will have profound implications for the developers. If the requirement is stated as only supervisors and personnel can view an employee record, the developer may end up coding an explicit test every time the application accesses this data. However, If the statement is only authorized users may access an employee record, the developer will probably design and implement some kind of access control system. When policy changes, and it will, only the metadata for that system will need to be updated. In fact, gathering requirements in this way naturally leads you to a system that is well factored to support metadata. In fact, there's a general rule here. Tip 79 policy is metadata. Implement the general case, with the policy information as an example of the type of thing the system needs to support. Requirements versus reality. In a January 1999 Wired magazine article, 71, producer and musician Brian Eno described an incredible piece of technology. The ultimate mixing board. It does anything to sound that can be done. And yet, instead of letting musicians make better music, or produce a recording faster or less expensively, it gets in the way, it disrupts the creative process. To see why, you have to look at how recording engineers work. They balance sounds intuitively. Over the years, they develop an innate feedback loop between their ears and their fingertips, sliding faders, rotating knobs, and so on. However, the interface to the new mixer didn't leverage off those abilities. Instead, it forced its users to type on a keyboard or click a mouse. The functions it provided were comprehensive, but they were packaged in unfamiliar and exotic ways. The functions the engineers needed were sometimes hidden behind obscure names, or were achieved with non-intuitive combinations of basic facilities. This example also illustrates our belief that successful tools adapt to the hands that use them. Successful requirements gathering takes this into account. And this is why early feedback, with prototypes or tracer bullets, will let your clients say yes, it does what I want, but not how I want. Documenting requirements. We believe that the best requirements documentation, perhaps the only requirements documentation, is working code. But that doesn't mean that you can get away without documenting your understanding of what the client wants. It just means that those documents are not a deliverable. They are not something that you give to a client to sign off on. Instead, they are simply mileposts to help guide the implementation process. Requirements documents are not for clients. In the past, both Andy and Dave have been on projects that produced incredibly detailed requirements. These substantial documents expanded on the client's initial 2-minute explanation of what was wanted, producing inch-thick masterpieces full of diagrams and tables. Things were specified to the point where there was almost no room for ambiguity in the implementation. Given sufficiently powerful tools, the document could actually be the final program. Creating these documents was a mistake for 2 reasons. First, as we've discussed, the client doesn't really know what they want up front. So when we take what they say and expand it into what is almost a legal document, we are building an incredibly complex castle on quicksand. You might say, but then we take the document to the client and they sign off on it. We're getting feedback. And that leads us to the second problem with these requirement specifications. The client never reads them. The client uses programmers because, while the client is motivated by solving a high-level and somewhat nebulous problem, programmers are interested in all the details and nuances. The requirements document is written for developers, and contains information and subtleties that are sometimes incomprehensible and frequently boring to the client. Submit a 200-page requirements document, and the client will likely heft it to decide if it weighs enough to be important. They may read the first couple of paragraphs, which is why the first 2 paragraphs are always titled Management Summary, and they may flick through the rest, sometimes stopping when there's a neat diagram. This isn't putting the client down. But giving them a large technical document is like giving the average developer a copy of the Iliad in Homeric Greek and asking them to code the video game from it. Requirements documents are for planning. So we don't believe in the monolithic, heavy enough to stune an ox, requirements document. We do, however, know that requirements have to be written down, simply because developers on a team need to know what they'll be doing. What form does this take? We favor something that can fit on a real, or virtual, index card. These short descriptions are often called user stories. They describe what a small portion of the application should do from the perspective of a user of that functionality. When written this way, the requirements can be placed on a board and moved around to show both status and priority. You might think that a single index card can't hold the information needed to implement a component of the application. You'd be right. And that's part of the point. By keeping this statement of requirements short, you're encouraging developers to ask clarifying questions. You're enhancing the feedback process between clients and coders before and during the creation of each piece of code. Overspecification. Another big danger in producing a requirements document is being too specific. Good requirements are abstract. Where requirements are concerned, the simplest statement that accurately reflects the business need is best. This doesn't mean you can be vague. You must capture the underlying semantic invariants as requirements, and document the specific or current work practices as policy. Requirements are not architecture. Requirements are not design, nor are they the user interface. Requirements are need. Just one more wafer-thin mint. Many project failures are blamed on an increase in scope, also known as feature bloat, creeping featureism, or requirements creep. This is an aspect of the boiled frog syndrome from Topic 4. Stone soup and boiled frogs. What can we do to prevent requirements from creeping up on us? The answer, again, is feedback. If you're working with the client in iterations with constant feedback, then the client will experience firsthand the impact of just one more feature. They'll see another story card go up on the board, and they'll get to help choose another card to move into the next iteration to make room. Feedback works both ways. Maintain a glossary as soon as you start discussing requirements. Users and domain experts will use certain terms that have specific meaning to them. They may differentiate between a client and a customer, for example. It would then be inappropriate to use either word casually in the system. Create and maintain a project glossary, one place that defines all the specific terms and vocabulary used in a project. All participants in the project, from end users to support staff, should use the glossary to ensure consistency. This implies that the glossary needs to be widely accessible, a good argument for online documentation. Tip 80. Use a project glossary. It's hard to succeed on a project if users and developers call the same thing by different names or, even worse, refer to different things by the same name. Related sections include Topic 5, Good Enough Software. Topic 7, Communicate. Topic 11, Reversibility. Topic 13, Prototypes and Post-it Notes. Topic 23, Design by Contract. Topic 43, Stay Safe Out There. Topic 44, Naming Things. Topic 46, Solving Impossible Puzzles. Topic 52, Delight Your Users. Exercises. Exercise 33, Possible Answer. Which of the following are probably genuine requirements? Restate those that are not to make them more useful, if possible. 1. The response time must be less than ~500 ms. 2. Modal windows will have a gray background. 3. The application will be organized as a number of front-end processes and a back-end server. 4. If a user enters non-numeric characters in a numeric field, the system will flash the field background and not accept them. 5. The code and data for this embedded application must fit within 32 megabits. Challenges. Can you use the software you are writing? Is it possible to have a good feel for requirements without being able to use the software yourself? Pick a non-computer-related problem you currently need to solve. Generate requirements for a non-computer solution. Topic 46, Solving Impossible Puzzles. Gordius, the king of Phrygia, once tied a knot that no one could untie. It was said that whoever solved the riddle of the Gordian knot would rule all of Asia. So along comes Alexander the Great, who chops the knot to bits with his sword. Just a little different interpretation of the requirements, that's all. And he did end up ruling most of Asia. Every now and again, You will find yourself embroiled in the middle of a project when a really tough puzzle comes up, some piece of engineering that you just can't get a handle on, or perhaps some bit of code that is turning out to be much harder to write than you thought. Maybe it looks impossible. But is it really as hard as it seems? Consider real-world puzzles, those devious little bits of wood, wrought iron, or plastic that seem to turn up as Christmas presents or at garage sales. All you have to do is remove the ring, or fit the shaped pieces in the box, or whatever. So you pull on the ring, or try to put the TS in the box, and quickly discover that the obvious solutions just don't work. The puzzle can't be solved that way. But even though it's obvious, that doesn't stop people from trying the same thing over and over, thinking there must be a way. Of course, there isn't. The solution lies elsewhere. The secret to solving the puzzle is to identify the real, not imagined, constraints, and find a solution therein. Some constraints are absolute, others are merely preconceived notions. Absolute constraints must be honored, however distasteful or stupid they may appear to be. On the other hand, as Alexander proved, some apparent constraints may not be real constraints at all. Many software problems can be just as sneaky. Degrees of freedom. The popular buzzphrase thinking outside the box encourages us to recognize constraints that might not be applicable and to ignore them. But this phrase isn't entirely accurate. If the box is the boundary of constraints and conditions, then the trick is to find the box, which may be considerably larger than you think. The key to solving puzzles is both to recognize the constraints placed on you and to recognize the degrees of freedom you do have, for in those you'll find your solution. This is why some puzzles are so effective, you may dismiss potential solutions too readily. For example, can you connect all of the dots in the following puzzle and return to the starting point with just 3 straight lines, without lifting your pen from the paper or retracing your steps? Math puzzles and games, Hall 92? You must challenge any preconceived notions and evaluate whether or not they are real, hard and fast constraints. It's not whether you think inside the box or outside the box. The problem lies in finding the box, identifying the real constraints. Tip 81: Don't think outside the box, find the box. When faced with an intractable problem, enumerate all the possible avenues you have before you. Don't dismiss anything, no matter how unusable or stupid it sounds. Now go through the list and explain why a certain path cannot be taken. Are you sure? Can you prove it? Consider the Trojan horse, a novel solution to an intractable problem. How do you get troops into a walled city without being discovered? You can bet that through the front door was initially dismissed as suicide. Categorize and prioritize your constraints. When woodworkers begin a project, they cut the longest pieces first, then cut the smaller pieces out of the remaining wood. In the same manner, we want to identify the most restrictive constraints first, and fit the remaining constraints within them. By the way, a solution to the 4 posts puzzle is shown at the end of the book. Get out of your own way. Sometimes you will find yourself working on a problem that seems much harder than you thought it should be. Maybe it feels like you're going down the wrong path, that there must be an easier way than this. Perhaps you are running late on the schedule now, or even despair of ever getting the system to work because this particular problem is impossible. This is an ideal time to do something else for a while. Work on something different. Go walk the dog. Sleep on it. Your conscious brain is aware of the problem, but your conscious brain is really pretty dumb, no offense. So it's time to give your real brain, that amazing associative neural net that lurks below your consciousness, some space. You'll be amazed how often the answer will just pop into your head when you deliberately distract yourself. If that sounds too mystical for you, it isn't. Psychology Today, 72, reports. To put it plainly, people who are distracted did better on a complex problem-solving task than people who put in conscious effort. If you're still not willing to drop the problem for a while, the next best thing is probably finding someone to explain it to. Often, the distraction of simply talking about it will lead you to enlightenment. Have them ask you questions such as, why are you solving this problem? What's the benefit of solving it? Are the problems you're having related to edge cases? Can you eliminate them? Is there a simpler, related problem you can solve? This is another example of rubber ducking in practice. Fortune favors the prepared mind. Louis Pasteur is reported to have said, Dans les champs de l'observation le hasard any favorise que les esprits prepares. When it comes to observation, fortune favors the prepared mind. That is true for problem solving, too. In order to have those eureka moments, your non-conscious brain needs to have plenty of raw material, prior experiences that can contribute to an answer. A great way to feed your brain is to give it feedback on what works and what doesn't work as you do your daily job. And we describe a great way to do that using an engineering daybook, topic 22, engineering daybooks. And always remember the advice on the cover of The Hitchhiker's Guide to the Galaxy, don't panic. Related sections include Topic 5, Good Enough Software. Topic 37, Listen to your lizard brain. Topic 45, The Requirements Pit. Andy wrote an entire book about this kind of thing, Pragmatic Thinking and Learning, Refactoring or Wetware, Hun 08. Challenges. Take a hard look at whatever difficult problem you are embroiled in today. Can you cut the Gordian knot? Do you have to do it this way? Do you have to do it at all? Were you handed a set of constraints when you signed on to your current project? Are they all still applicable, and is the interpretation of them still valid? Topic 47, Working Together. It was one of those impossible projects, the kind you hear about. I've never met a that sounds both exhilarating and human being who terrifying at the same time. And would want to read. Ancient system was approaching 17,000 pages of end of life. The hardware was documentation, and if they're physically going away, I'd kill him to get brand new system had to be him out of the crafted that would match the gene pool of the undocumented behavior exactly. Many hundreds of millions of dollars of other Joseph Costello, president of Cadence People's money would pass through this system, and the deadline from inception to deployment was on the order of months. And that is where Andy and Dave first met. An impossible project with a ridiculous deadline. There was only one thing that made the project a roaring success. The expert who had managed this system for years was sitting right there in her office, just across the hall from our broom closet-sized development room. Continuously available for questions, clarifications, decisions, and demos. Throughout this book we recommend working closely with users. They are part of your team. On that first project together, we practiced what now might be called pair programming or mob programming, one person typing code while one or more other team members comment, ponder, and solve problems together. It's a powerful way of working together that transcends endless meetings, memos, and overstuffed legalistic documentation prized for weight over usefulness. And that's what we really mean by working with, not just asking questions, having discussions, and taking notes, but asking questions and having discussions while you're actually coding. Conway's Law. In 1967, Melvin Conway introduced an idea in How Do Committees Invent? Con 68, which would become known as Conway's Law. Organizations which design systems are constrained to produce designs which are copies of the communication structures of these organizations. That is, the social structures and communication pathways of the team and the organization will be mirrored in the application, website, or product being developed. Various studies have shown strong support for this idea. We've witnessed it firsthand countless times, for example, in teams where no one talks to each other at all, resulting in siloed, stovepipe systems. Or teams that were split into two, resulting in a client, server or front-end back-end division. Studies also offer support for the reverse principle. You can deliberately structure your team the way you want your code to look. For example, geographically distributed teams are shown to tend toward more modular, distributed software. But most importantly, development teams that include users will produce software that clearly reflects that involvement, and teams that don't bother will reflect that, too. Pair programming. Pair programming is one of the practices of extreme programming that has become popular outside of XP itself. In pair programming, one developer operates the keyboard, and the other does not. Both work on the problem together, and can switch typing duties as needed. There are many benefits to pair programming. Different people bring different backgrounds and experience, different problem-solving techniques and approaches, and differing levels of focus and attention to any given problem. The developer acting as typist must focus on the low-level details of syntax and coding style, while the other developer is free to consider higher-level issues and scope. While that might sound like a small distinction, remember that we humans have only so much brain bandwidth. Fiddling around with typing esoteric words and symbols that the compiler will grudgingly accept takes a fair bit of our own processing power. Having a second developer's full brain available during the task brings a lot more mental power to bear. The inherent peer pressure of a second person helps against moments of weakness and bad habits of naming variables foo and such. You're less inclined to take a potentially embarrassing shortcut when someone is actively watching, which also results in higher quality software. Mob programming. And if two heads are better than one, what about having a dozen diverse people all working on the same problem at the same time, with one typist? Mob programming, despite the name, does not involve torches or pitchforks. It's an extension of pair programming that involves more than just two developers. Proponents report great results using mobs to solve hard problems. Mobs can easily include people not usually considered part of the development team, including users, project sponsors, and testers. In fact, in our first Impossible project together, it was a common sight for one of us to be typing while the other discussed the issue with our business expert. It was a small mob of 3. You might think of mob programming as tight collaboration with live coding. What should I do? If you're currently only programming solo, maybe try pair programming. Give it a minimum of 2 weeks, only a few hours at a time, as it will feel strange at first. To brainstorm new ideas or diagnose thorny issues, perhaps try a mob programming session. If you are already pairing or mobbing, who's included? Is it just developers, or do you allow members of your extended team to participate, users, testers, sponsors? And as with all collaboration, you need to manage the human aspects of it as well as the technical. Here are just a few tips to get started. Build the code, not your ego. It's not about who's brightest, we all have our moments, good and bad. Start small. Mob with only 4 to 5 people, or start with just a few pairs, in short sessions. Criticize the code, not the person. Let's look at this block sounds much better than you're wrong. Listen and try to understand others' viewpoints. Different isn't wrong. Conduct frequent retrospectives to try and improve for next time. Coding in the same office or remote, alone, in pairs, or in mobs, are all effective ways of working together to solve problems. If you and your team have only ever done it one way, you might want to experiment with a different style. But don't just jump in with a naive approach, there are rules, suggestions, and guidelines for each of these development styles. For instance, with mob programming you swap out the typist every 5 to 10 minutes. Do some reading and research, from both textbook and experience reports, and get a feel for the advantages and pitfalls you may encounter. You might want to start by coding a simple exercise, and not just jump straight into your toughest production code. But however you go about it, let us suggest one final piece of advice. Tip 82: Don't go into the code alone. Tip 83: Agile is not a noun, agile is how you do things. As we write this, almost 20 years after the inception of the Manifesto for Agile Software Development, 73, we see many developers successfully applying its values. We see many fantastic teams who find ways to take these values and use them to guide what they do, and how they change what they do. But we also see another side of agility. We see teams and companies eager for off-the-shelf solutions, agile in a box. And we see many consultants and companies all too happy to sell them what they want. We see companies adopting more layers of management, more formal reporting, more specialized developers, and more fancy job titles, which just mean someone with a clipboard and a stopwatch. 74. You keep using that word, I do not think it. Means what you think it means. Inigo Montoya, The Princess Bride. Topic 48. The essence of agility. Agile is an adjective. It's how you do something. You can be an agile developer. You can be on a team that adopts agile practices, a team that responds to change and setbacks with agility. Agility is your style, not you. We feel that many people have lost sight of the true meaning of agility, and would like to see folks return to the basics. Remember the values from the manifesto. We are uncovering better ways of developing software by doing it and helping others do it. Through this work we have come to value individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, responding to change over following a plan. That is, while there is value in the items on the right, we value the items on the left more. Anyone selling you something that increases the importance on things on the right over things on the left clearly doesn't value the same things that we and the other manifesto writers did. And anyone selling you a solution in a box hasn't read the introductory statement. The values are motivated and informed by the continuous act of uncovering better ways to produce software. This is not a static document. It's suggestions for a generative process. There can never be an agile process. In fact, whenever someone says do this, and you'll be agile, they are wrong. By definition. Because agility, both in the physical world and in software development, is all about responding to change, responding to the unknowns you encounter after you set out. A running gazelle doesn't go in a straight line. A gymnast makes hundreds of corrections a second as they respond to changes in their environment and minor errors in their foot placement. So it is with teams and individual developers. There is no single plan you can follow when you develop software. 3 of the 4 values tell you that. They are all about gathering and responding to feedback. The values don't tell you what to do. They tell you what to look for when you decide for yourself what to do. These decisions are always contextual. They depend on who you are, the nature of your team, your application, your tooling, your company, your customer, the outside world, an incredibly large number of factors, some major and some trivial. No fixed, static plan can survive this uncertainty. So what do we do? No one can tell you what to do. But we think we can tell you something about the spirit with which you do it. It all boils down to how you deal with uncertainty. The manifesto suggests that you do this by gathering and acting on feedback. So here's our recipe for working in an agile way. 1. Work out where you are. 2. Make the smallest meaningful step towards where you want to be. 3. Evaluate where you end up, and fix anything you broke. Repeat these steps until you're done. And use them recursively, at every level of everything you do. Sometimes even the most trivial seeming decision becomes important when you gather feedback. Now my code needs to get the account owner. Let user equals account owner, account ID. User is a useless name. I'll make it owner. Let owner equals account owner, account ID, but now that feels a little redundant. What am I actually trying to do here? The story says that I'm sending this person an email, so I need to find their email address. Maybe I don't need the whole account owner at all. Let email equals email of account owner, account ID. By applying the feedback loop at a really low level, the naming of a variable, we've actually improved the design of the overall system, reducing the coupling between this code and the code that deals with accounts. The feedback loop also applies at the highest level of a project. Some of our most successful work has happened when we started working on a client's requirements, took a single step, and realized that what we were about to do wasn't necessary, that the best solution didn't even involve software. This loop applies outside the scope of a single project. Teams should apply it to review their process and how well it worked. A team that doesn't continuously experiment with their process is not an agile team. And this drives design. In Topic 8, The Essence of Good Design, we assert that the measure of design is how easy the result of that design is to change. A good design produces something that's easier to change than a bad design. And this discussion about agility explains why that's the case. You make a change, and discover you don't like it. Step 3 in our list says we have to be able to fix what we break. To make our feedback loop efficient, this fix has to be as painless as possible. If it isn't, we'll be tempted to shrug it off and leave it unfixed. We talk about this effect in Topic 3, Software Entropy. To make this whole agile thing work, we need to practice good design, because good design makes things easy to change. And if it's easy to change, we can adjust, at every level, without any hesitation. That is agility. Related sections include Topic 27, Don't Outrun Your Headlights, Topic 40, Refactoring, Topic 50, Coconuts Don't Cut It. Challenges. The simple feedback loop isn't just for software. Think of other decisions you've made recently. Could any of them have been improved by thinking about how you might be able to undo them if things didn't take you in the direction you were going? Can you think of ways you can improve what you do by gathering and acting on feedback? Chapter 9. Pragmatic Projects. As your project gets underway, we need to move away from issues of individual philosophy and coding to talk about larger, project-sized issues. We aren't going to go into specifics of project management, but we will talk about a handful of critical areas that can make or break any project. As soon as you have more than one person working on a project, you need to establish some ground rules and delegate parts of the project accordingly. In Topic 49, Pragmatic Teams, we'll show how to do this while honoring the pragmatic philosophy. The purpose of a software development method is to help people work together. Are you and your team doing what works well for you, or are you only investing in the trivial surface artifacts, and not getting the real benefits you deserve? We'll see why Topic 50, Coconuts Don't Cut It, and offer the true secret to success. And of course, none of that matters if you can't deliver software consistently and reliably. That's the basis of the magic trio of version control, testing, and automation, the Topic 51, Pragmatic Starter Kit. Ultimately, though, success is in the eye of the beholder, the sponsor of the project. The perception of success is what counts, and in Topic 52, Delight Your Users, will show you how to delight every project sponsor. The last tip in the book is a direct consequence of all the rest. In Topic 53, Pride and Prejudice, we ask you to sign your work, and to take pride in what you do. Topic 49, Pragmatic Teams. Even in 1985, the joke about herding cats was getting old. Bayat Group L. Stoffel, the time of the first edition at the overseas 6 first-rate turn of the century, it was. Programmers are positively ancient. Yet it persists, managerial challenge, because it has a ring of truth to it. Roughly comparable to programmers are a bit like cats, herding cats. Intelligent, strong-willed, opinionated, independent, and the Washington Post often worshipped by the net. Magazine, June 9, 1985. So far in this book we've looked at pragmatic techniques that help an individual be a better programmer. Can these methods work for teams as well, even for teams of strong-willed, independent people? The answer is a resounding yes. There are advantages to being a pragmatic individual, but these advantages are multiplied manyfold if the individual is working on a pragmatic team. A team, in our view, is a small, mostly stable entity of its own. 50 people aren't a team, they are a horde. 75 teams where members are constantly being pulled onto other assignments and no one knows each other aren't a team either, they are merely strangers temporarily sharing a bus stop in the rain. A pragmatic team is small, under 10 to 12 or so members. Members come and go rarely. Everyone knows everyone well, trusts each other, and depends on each other. Tip 84. Maintain small, stable teams. In this section we'll look briefly at how pragmatic techniques can be applied to teams as a whole. These notes are only a start. Once you've got a group of pragmatic developers working in an enabling environment, they'll quickly develop and refine their own team dynamics that work for them. Let's recast some of the previous sections in terms of teams. No broken windows. Quality is a team issue. The most diligent developer placed on a team that just doesn't care will find it difficult to maintain the enthusiasm needed to fix niggling problems. The problem is further exacerbated if the team actively discourages the developer from spending time on these fixes. Teams as a whole should not tolerate broken windows, those small imperfections that no one fixes. The team must take responsibility for the quality of the product, supporting developers who understand the no broken windows philosophy we describe in Topic 3, Software Entropy, and encouraging those who haven't yet discovered it. Some team methodologies have a quality officer, someone to whom the team delegates the responsibility for the quality of the deliverable. This is clearly ridiculous. Quality can come only from the individual contributions of all team members. Quality is built in, not bolted on. Boiled frogs. Remember the apocryphal frog in the pan of water, back in Topic 4, Stone Soup and Boiled Frogs? It doesn't notice the gradual change in its environment, and ends up cooked. The same can happen to individuals who aren't vigilant. It can be difficult to keep an eye on your overall environment in the heat of project development. It's even easier for teams as a whole to get boiled. People assume that someone else is handling an issue, or that the team leader must have okayed a change that your user is requesting. Even the best-intentioned teams can be oblivious to significant changes in their projects. Fight this. Encourage everyone to actively monitor the environment for changes. Stay awake and aware for increased scope, decreased timescales, additional features, new environments, anything that wasn't in the original understanding. Keep metrics on new requirements. 76. The team needn't reject changes out of hand, you simply need to be aware that they're happening. Otherwise, it'll be you in the hot water. Schedule your knowledge portfolio. In Topic 6, Your Knowledge Portfolio, we looked at ways you should invest in your personal knowledge portfolio on your own time. Teams that want to succeed need to consider their knowledge and skill investments as well. If your team is serious about improvement and innovation, you need to schedule it. Trying to get things done whenever there's a free moment means they will never happen. Whatever sort of backlog or task list or flow you're working with, don't reserve it for only feature development. The team works on more than just new features. Some possible examples include old systems maintenance. While we love working on the shiny new system, there's likely maintenance work that needs to be done on the old system. We've met teams who try and shove this work in the corner. If the team is charged with doing these tasks, then do them for real. Process reflection and refinement. Continuous improvement can only happen when you take the time to look around, figure out what's working and not, and then make changes. See Topic 48, The Essence of Agility. Too many teams are so busy bailing out water that they don't have time to fix the leak. Schedule it. Fix it. New tech experiments. Don't adopt new tech, frameworks, or libraries just because everyone is doing it, or based on something you saw at a conference or read online. Deliberately vet candidate technologies with prototypes. Put tasks on the schedule to try the new things and analyze results. Learning and skill improvements. Personal learning and improvements are a great start, but many skills are more effective when spread team-wide. Plan to do it, whether it's the informal brown bag lunch or more formal training sessions. Tip 85. Schedule it to make it happen. Communicate team presence. It's obvious that developers in a team must talk to each other. We gave some suggestions to facilitate this in Topic 7, Communicate. However, it's easy to forget that the team itself has a presence within the organization. The team as an entity needs to communicate clearly with the rest of the world. To outsiders, the worst project teams are those that appear sullen and reticent. They hold meetings with no structure, where no one wants to talk. Their emails and project documents are a mess, no two look the same, and each uses different terminology. Great project teams have a distinct personality. People look forward to meetings with them, because they know that they'll see a well-prepared performance that makes everyone feel good. The documentation they produce is crisp, accurate, and consistent. The team speaks with one voice, 77, they may even have a sense of humor. There is a simple marketing trick that helps teams communicate as one: generate a brand. When you start a project, come up with a name for it, ideally something off the wall. In the past, we've named projects after things such as killer parrots that prey on sheep, optical illusions, gerbils, cartoon characters, and mythical cities. Spend 30 minutes coming up with a zany logo, and use it. Use your team's name liberally when talking with people. It sounds silly, but it gives your team an identity to build on, and the world something memorable to associate with your work. Don't repeat yourselves. In Topic 9, DIY, the Evils of Duplication, we talked about the difficulties of eliminating duplicated work between members of a team. This duplication leads to wasted effort, and can result in a maintenance nightmare. Stovepipe or siloed systems are common in these teams, with little sharing and a lot of duplicated functionality. Good communication is key to avoiding these problems. And by good we mean instant and frictionless. You should be able to ask a question of team members and get a more or less instant reply. If the team is co-located, this might be as simple as poking your head over the cube wall or down the hall. For remote teams, you may have to rely on a messaging app or other electronic means. If you have to wait a week for the team meeting to ask your question or share your status, that's an awful lot of friction. 78. Frictionless means it's easy and low ceremony to ask questions, share your progress, your problems, your insights and learnings, and to stay aware of what your teammates are doing. Maintain awareness to stay DIY. Team tracer bullets. A project team has to accomplish many different tasks in different areas of the project, touching a lot of different technologies. Understanding requirements, designing architecture, coding for front-end and server, testing, all have to happen. But it's a common misconception that these activities and tasks can happen separately, in isolation. They can't. Some methodologies advocate all sorts of different roles and titles within the team, or create separate specialized teams entirely. But the problem with that approach is that it introduces gates and handoffs. Now instead of a smooth flow from the team to deployment, you have artificial gates where the work stops. Handoffs that have to wait to be accepted. Approvals. Paperwork. The lean folks call this waste, and strive to actively eliminate it. All of these different roles and activities are actually different views of the same problem, and artificially separating them can cause a boatload of trouble. For example, programmers who are 2 or 3 levels removed from the actual users of their code are unlikely to be aware of the context in which their work is used. They will not be able to make informed decisions. With Topic 12, tracer bullets, we recommend developing individual features, however small and limited initially, that go end-to-end through the entire system. That means that you need all the skills to do that within the team: front-end, UI/UX, server, DBA, QA, etc., all comfortable and accustomed to working with each other. With a tracer bullet approach, you can implement very small bits of functionality very quickly, and get immediate feedback on how well your team communicates and delivers. That creates an environment where you can make changes and tune your team and process quickly and easily. Tip 86: Organize fully functional teams. Build teams so you can build code end-to-end, incrementally and iteratively. Automation: a great way to ensure both consistency and accuracy is to automate everything the team does. Why struggle with code formatting standards when your editor or IDE can do it for you automatically? Why do manual testing when the continuous build can run tests automatically? Why deploy by hand when automation can do it the same way every time, repeatably and reliably? Automation is an essential component of every project team. Make sure the team has skills at tool building to construct and deploy the tools that automate the project development and production deployment. Know when to stop adding paint. Remember that teams are made up of individuals. Give each member the ability to shine in their own way. Give them just enough structure to support them and to ensure that the project delivers value. Then, like the painter in topic 5, good enough software, resist the temptation to add more paint. Related sections include Topic 2, the cat ate my source code. Topic 7, communicate. Topic 12, tracer bullets. Topic 19, version control. Topic 50, coconuts don't cut it. Topic 51, Pragmatic Starter Kit. Challenges. Look around for successful teams outside the area of software development. What makes them successful? Do they use any of the processes discussed in this section? Next time you start a project, try convincing people to brand it. Give your organization time to become used to the idea, and then do a quick audit to see what difference it made, both within the team and externally. You were probably once given problems such as if it takes 4 workers 6 hours to dig a ditch, how long would it take 8 workers? In real life, however, what factors affect the answer if the workers were writing code instead? In how many scenarios is the time actually reduced? Read The Mythical Man Month, Bro 96, by Frederick Brooks. For extra credit, buy 2 copies so you can read it twice as fast. The native islanders had never seen an airplane before, or met people such as these strangers. In return for use of their land, the strangers provided mechanical birds that flew in and out all day long on a runway, bringing incredible material wealth to their island home. The strangers mentioned something about war and fighting. One day it was over and they all left, taking their strange riches with them. The islanders were desperate to restore their good fortunes, and rebuilt a facsimile of the airport, control tower, and equipment using local materials, vines, coconut shells, palm fronds, and such. But for some reason, even though they had everything in place, the planes didn't come. They had imitated the form, but not the content. Anthropologists call this a cargo cult. All too often, we are the islanders. It's easy and tempting to fall into the cargo cult trap. By investing in and building up the easily visible artifacts, you hope to attract the underlying, working magic. But as with the original cargo cults of Melanesia, 79, a fake airport made out of coconut shells is no substitute for the real thing. For example, we have personally seen teams that claim to be using Scrum. But, upon closer examination, it turned out they were doing a daily stand-up meeting once a week, with 4-week iterations that often turned into 6 or 8-week iterations. They felt that this was okay because they were using a popular agile scheduling tool. They were only investing in the Topic 50 Coconuts don't cut it. Superficial artifacts, and even then, often in name only, as if stand-up or iteration was some sort of incantation for the superstitious. Unsurprisingly, they, too, failed to attract the real magic. Context matters. Have you or your team fallen in this trap? Ask yourself, why are you even using that particular development method? Or that framework? Or that testing technique? Is it actually well suited for the job at hand? Does it work well for you? Or was it adopted just because it was being used by the latest internet-fueled success story? There's a current trend to adopt the policies and processes of successful companies such as Spotify, Netflix, Stripe, GitLab, and others. Each have their own unique take on software development and management. But consider the context. Are you in the same market, with the same constraints and opportunities, similar expertise and organization size, similar management, and similar culture? Similar user base and requirements? Don't fall for it. Particular artifacts, superficial structures, policies, processes, and methods are not enough. Tip 87 Do what works, not what's fashionable. How do you know what works? You rely on that most fundamental of pragmatic techniques. Try it. Pilot the idea with a small team or set of teams. Keep the good bits that seem to work well, and discard anything else as waste or overhead. No one will downgrade your organization because it operates differently from Spotify or Netflix, because even they didn't follow their current processes while they were growing. And years from now, as those companies mature and pivot and continue to thrive, they'll be doing something different yet again. That's the actual secret to their success. One size fits no one well. The purpose of a software development methodology is to help people work together. As we discuss in topic 48, the essence of agility, there is no single plan you can follow when you develop software, especially not a plan that someone else came up with at another company. Many certification programs are actually even worse than that. They are predicated on the student being able to memorize and follow the rules. But that's not what you want. You need the ability to see beyond the existing rules and exploit possibilities for advantage. That's a very different mindset from but Scrum, Lean, Kanban, XP, Agile does it this way. And so on. Instead, you want to take the best pieces from any particular methodology and adapt them for use. No one size fits all, and current methods are far from complete, so you'll need to look at more than just one popular method. For example, Scrum defines some project management practices, but Scrum by itself doesn't provide enough guidance at the technical level for teams or at the portfolio governance level for leadership. So where do you start? The real goal. The goal, of course, isn't to do Scrum, do Agile, do Lean, or what have you. The goal is to be in a position to deliver working software that gives the users some new capability at a moment's notice. Not weeks, months, or years from now, but now. For many teams and organizations, continuous delivery feels like a lofty, unattainable goal, especially if you're saddled with a process that restricts delivery to months, or even weeks. But as with any goal, the key is to keep aiming in the right direction. Images delivery_times.png. If you're delivering in years, try and shorten the cycle to months. From months, cut it down to weeks. From a 4-week. Be like them. We frequently hear software development leaders tell their staff, we should operate like Netflix, or one of these other leading companies. Of course you could do that. First, get yourself a few 100,000 servers and tens of millions of users. Sprint, try 2. From a 2-week sprint, try 1. Then daily. Then, finally, on demand. Note that being able to deliver on demand does not mean you are forced to deliver every minute of every day. You deliver when the users need it, when it makes business sense to do so. Tip 88: deliver when users need it. In order to move to this style of continuous development, you need a rock-solid infrastructure, which we discuss in the next topic, topic 51, Pragmatic Starter Kit. You do development in the main trunk of your version control system, not in branches, and use techniques such as feature switches to roll out test features to users selectively. Once your infrastructure is in order, you need to decide how to organize the work. Beginners might want to start with Scrum for project management, plus the technical practices from Extreme Programming, XP. More disciplined and experienced teams might look to Kanban and Lean techniques, both for the team and perhaps for larger governance issues. But don't take our word for it, investigate and try these approaches for yourself. Be careful, though, in overdoing it. Overly investing in any particular methodology can leave you blind to alternatives. You get used to it. Soon it becomes hard to see any other way. You've become calcified, and now you can't adapt quickly anymore. Might as well be using coconuts. Related sections include Topic 12, Tracer Bullets. Topic 27, Don't outrun your headlights. Topic 48, The essence of agility. Topic 49, Pragmatic Teams. Topic 51, Pragmatic Starter Kit. Topic 51, Pragmatic Starter Kit. Back when cars were a novelty, the instructions for starting a Model T civilization advances forward were more than 2 pages by extending the long. With modern cars, you just number of important push a button, the starting operations we can procedure is automatic and perform without foolproof. A person following a list thinking of instructions might flood the engine, but the automatic starter Alfred North Whitehead won't. Although software development is still an industry at the Model T stage, we can't afford to go through 2 pages of instructions again and again for some common operation. Whether it is the build and release procedure, testing, project paperwork, or any other recurring task on the project, it has to be automatic and repeatable on any capable machine. In addition, we want to ensure consistency and repeatability on the project. Manual procedures leave consistency up to chance. Repeatability isn't guaranteed, especially if aspects of the procedure are open to interpretation by different people. After we wrote the first edition of the Pragmatic Programmer, we wanted to create more books to help teams develop software. We figured we should start at the beginning. What are the most basic, most important elements that every team needs regardless of methodology, language, or technology stack? And so the idea of the Pragmatic Starter Kit was born, covering these 3 critical and interrelated topics: version control, regression testing, full automation. These are the 3 legs that support every project. Here's how. Drive with version control. As we said in topic 19, version control, you want to keep everything needed to build your project under version control. That idea becomes even more important in the context of the project itself. First, it allows build machines to be ephemeral. Instead of one hallowed, creaky machine in the corner of the office that everyone is afraid to touch, 80 build machines and or clusters are created on demand as spot instances in the cloud. Deployment configuration is under version control as well, so releasing to production can be handled automatically. And that's the important part. At the project level, version control drives the build and release process. Tip 89: use version control to drive builds, tests, and releases. That is, build, test, and deployment are triggered via commits or pushes to version control, and built in a container in the cloud. Release to staging or production is specified by using a tag in your version control system. Releases then become a much more low-ceremony part of everyday life, true continuous delivery, not tied to any one build machine or developer's machine. Ruthless and continuous testing. Many developers test gently, subconsciously knowing where the code will break and avoiding the weak spots. Pragmatic programmers are different. We are driven to find our bugs now, so we don't have to endure the shame of others finding our bugs later. Finding bugs is somewhat like fishing with a net. We use fine, small nets, unit tests, to catch the minnows, and big, coarse nets, integration tests, to catch the killer sharks. Sometimes the fish manage to escape, so we patch any holes that we find, in hopes of catching more and more slippery defects that are swimming about in our project pool. Tip 90: test early, test often, test automatically. We want to start testing as soon as we have code. Those tiny minnows have a nasty habit of becoming giant, man-eating sharks pretty fast, and catching a shark is quite a bit harder. So we write unit tests. A lot of unit tests. In fact, a good project may well have more test code than production code. The time it takes to produce this test code is worth the effort. It ends up being much cheaper in the long run, and you actually stand a chance of producing a product with close to 0 defects. Additionally, knowing that you've passed the test gives you a high degree of confidence that a piece of code is done. Tip 91: coding ain't done till all the tests run. The automatic build runs all available tests. It's important to aim to test for real. In other words, the test environment should match the production environment closely. Any gaps are where bugs breed. The build may cover several major types of software testing: unit testing, integration testing, validation and verification, and performance testing. This list is by no means complete, and some specialized projects will require various other types of testing as well. But it gives us a good starting point. Unit testing. A unit test is code that exercises a module. We covered this in topic 41, Test to Code. Unit testing is the foundation of all the other forms of testing that we'll discuss in this section. If the parts don't work by themselves, they probably won't work well together. All of the modules you are using must pass their own unit tests before you can proceed. Once all of the pertinent modules have passed their individual tests, you're ready for the next stage. You need to test how all the modules use and interact with each other throughout the system. Integration testing. Integration testing shows that the major subsystems that make up the project work and play well with each other. With good contracts in place and well tested, any integration issues can be detected easily. Otherwise, integration becomes a fertile breeding ground for bugs. In fact, it is often the single largest source of bugs in the system. Integration testing is really just an extension of the unit testing we've described. You're just testing how entire subsystems honor their contracts. Validation and verification. As soon as you have an executable user interface or prototype, you need to answer an all-important question. The users told you what they wanted, but is it what they need? Does it meet the functional requirements of the system? This, too, needs to be tested. A bug-free system that answers the wrong question isn't very useful. Be conscious of end-user access patterns and how they differ from developer test data. For an example, see the story about brush strokes here. Performance testing. Performance or stress testing may be important aspects of the project as well. Ask yourself if the software meets the performance requirements under real-world conditions, with the expected number of users, or connections, or transactions per second. Is it scalable? For some applications, you may need specialized testing hardware or software to simulate the load realistically. Testing the tests. Because we can't write perfect software, it follows that we can't write perfect test software either. We need to test the tests. Think of our set of test suites as an elaborate security system, designed to sound the alarm when a bug shows up. How better to test a security system than to try to break in? After you have written a test to detect a particular bug, cause the bug deliberately and make sure the test complains. This ensures that the test will catch the bug if it happens for real. Tip 92. Use saboteurs to test your testing. If you are really serious about testing, take a separate branch of the source tree, introduce bugs on purpose, and verify that the tests will catch them. At a higher level, you can use something like Netflix's Chaos Monkey 81 to disrupt, i.e., kill, services and test your application's resilience. When writing tests, make sure that alarms sound when they should. Testing thoroughly. Once you are confident that your tests are correct, and are finding bugs you create, how do you know if you have tested the code base thoroughly enough? The short answer is you don't, and you never will. You might look to try coverage analysis tools that watch your code during testing and keep track of which lines of code have been executed and which haven't. These tools help give you a general feel for how comprehensive your testing is, but don't expect to see 100% coverage. 82. Even if you do happen to hit every line of code, that's not the whole picture. What is important is the number of states that your program may have. States are not equivalent to lines of code. For instance, suppose you have a function that takes two integers, each of which can be a number from 0 to 999. Int test, int a, int b, return a plus b. In theory, this three-line function has 1 million logical states, 999,999 of which will work correctly and one that will not, when a plus b equals 0. Simply knowing that you executed this line of code doesn't tell you that you would need to identify all possible states of the program. Unfortunately, in general this is a really hard problem. Hard as in, the sun will be a cold hard lump before you can solve it. Tip 93. Test state coverage, not code coverage. Property-based testing. A great way to explore how your code handles unexpected states is to have a computer generate those states. Use property-based testing techniques to generate test data according to the contracts and invariants of the code under test. We cover this topic in detail in Topic 42, Property-based testing. Tightening the net. Finally, we'd like to reveal the single most important concept in testing. It is an obvious one, and virtually every textbook says to do it this way. But for some reason, most projects still do not. If a bug slips through the net of existing tests, you need to add a new test to trap it next time. Tip 94. Find bugs once. Once a human tester finds a bug, it should be the last time a human tester finds that bug. The automated tests should be modified to check for that particular bug from then on, every time, with no exceptions, no matter how trivial, and no matter how much the developer complains and says, "Oh, that will never happen again." Because it will happen again. And we just don't have the time to go chasing after bugs that the automated tests could have found for us. We have to spend our time writing new code and new bugs. Full automation. As we said at the beginning of this section, modern development relies on scripted, automatic procedures. Whether you use something as simple as shell scripts with RSYNC and SSH, or full-featured solutions such as Ansible, Puppet, Chef, or Salt, just don't rely on any manual intervention. Once upon a time, we were at a client site where all the developers were using the same IDE. Their system administrator gave each developer a set of instructions on installing add-on packages to the IDE. These instructions filled many pages full of click here, scroll there, drag this, double-click that, and do it again. Not surprisingly, every developer's machine was loaded slightly differently. Subtle differences in the application's behavior occurred when different developers ran the same code. Bugs would appear on one machine but not on others. Tracking down version differences of any one component usually revealed a surprise. Tip 95. Don't use manual procedures. People just aren't as repeatable as computers are. Nor should we expect them to be. A shell script or program will execute the same instructions, in the same order, time after time. It is under version control itself, so you can examine changes to the build-release procedures over time as well, but it used to work. Everything depends on automation. You can't build the project on an anonymous cloud server unless the build is fully automatic. You can't deploy automatically if there are manual steps involved. And once you introduce manual steps, just for this one part, you've broken a very large window, 83. With these three legs of version control, ruthless testing, and full automation, your project will have the firm foundation you need so you can concentrate on the hard part, delighting users. Related sections include Topic 11, Reversibility. Topic 12, Traceability. Topic 17, Shell Games. Topic 19, Version Control. Topic 41, Test to Code. Topic 49, Pragmatic Teams. Topic 50, Coconuts Don't Cut It. Challenges. Are your nightly or continuous builds automatic, but deploying to production isn't? Why? What's special about that server? Can you automatically test your project completely? Many teams are forced to answer no. Why? Is it too hard to define the acceptable results? Won't this make it hard to prove to the sponsors that the project is done? Is it too hard to test the application logic independent of the GUI? What does this say about the GUI? About coupling? Topic 52. Delight your users. Our goal as developers is to delight users. That's why we're here. Not when you enchant to mine them for their data, or people. Your goal is not count their eyeballs or empty their to make money wallets. Nefarious goals aside, from them all to get even delivering working software them to do what you in a timely manner isn't enough. Want, but that alone won't delight them. To fill them with great delight. Your users are not particularly motivated by code. Instead, they have a business problem that Guy Kawasaki needs solving within the context of their objectives and budget. Their belief is that by working with your team they'll be able to do this. Their expectations are not software-related. They aren't even implicit in any specification they give you, because that specification will be incomplete until your team has iterated through it with them several times. How do you unearth their expectations, then? Ask a simple question. How will you know that we've all been successful a month, or a year, or whatever, after this project is done? You may well be surprised by the answer. A project to improve product recommendations might actually be judged in terms of customer retention. A project to consolidate 2 databases might be judged in terms of data quality, or it might be about cost savings. But it's these expectations of business value that really count, not just the software project itself. The software is only a means to these ends. And now that you've surfaced some of the underlying expectations of value behind the project, you can start thinking about how you can deliver against them. Make sure everyone on the team is totally clear about these expectations. When making decisions, think about which path forward moves closer to those expectations. Critically analyze the user requirements in light of the expectations. On many projects we've discovered that the stated requirement was in fact just a guess at what could be done by technology. It was actually an amateur implementation plan dressed up as a requirements document. Don't be afraid to make suggestions that change the requirement if you can demonstrate that they will move the project closer to the objective. Continue to think about these expectations as you progress through the project. We've found that as our knowledge of the domain increases, we're better able to make suggestions on other things that could be done to address the underlying business issues. We strongly believe that developers, who are exposed to many different aspects of an organization, can often see ways of weaving different parts of the business together that aren't always obvious to individual departments. Tip 96: Delight users, don't just deliver code. If you want to delight your client, forge a relationship with them where you can actively help solve their problems. Even though your title might be some variation of software developer or software engineer, in truth it should be problem solver. That's what we do, and that's the essence of a pragmatic programmer. We solve problems. Related sections include Topic 12, Tracer bullets. Topic 13, Prototypes and post-it notes. Topic 45, The requirements pit. Topic 53, Pride and prejudice. Pragmatic programmers don't shirk from responsibility. Instead, you have delighted us. We rejoice in accepting challenges long enough, and in making our expertise well known. If we are responsible for a Jane Austen, Pride and Design, or a piece of code, we do a prejudiced job we can be proud of. Tip 97: Sign your work. Artisans of an earlier age were proud to sign their work. You should be, too. Project teams are still made up of people, however, and this rule can cause trouble. On some projects, the idea of code ownership can cause cooperation problems. People may become territorial, or unwilling to work on common foundation elements. The project may end up like a bunch of insular little fiefdoms. You become prejudiced in favor of your code and against your coworkers. That's not what we want. You shouldn't jealously defend your code against interlopers. By the same token, you should treat other people's code with respect. The golden rule: do unto others as you would have them do unto you, and a foundation of mutual respect among the developers is critical to make this tip work. Anonymity, especially on large projects, can provide a breeding ground for sloppiness, mistakes, sloth, and bad code. It becomes too easy to see yourself as just a cog in the wheel, producing lame excuses in endless status reports instead of good code. While code must be owned, it doesn't have to be owned by an individual. In fact, Kent Beck's Extreme Programming, 84, recommends communal ownership of code, but this also requires additional practices, such as pair programming, to guard against the dangers of anonymity. We want to see pride of ownership. I wrote this, and I stand behind my work. Your signature should come to be recognized as an indicator of quality. People should see your name on a piece of code and expect it to be solid, well written, tested, and documented. A really professional job. Written by a professional. A pragmatic programmer. Thank you. In the long run, we shape our lives, and we shape ourselves. The process never ends until we die. And the choices we make are ultimately our own. Responsibility. Eleanor Roosevelt. Chapter 10. Postface. In the 20 years leading up to the first edition, we were part of the evolution of the computer from a peripheral curiosity to a modern imperative for businesses. In the 20 years since then, software has grown beyond mere business machines and has truly taken over the world. But what does that really mean for us? In the Mythical Man Month, Essays on Software Engineering, Bro 96, Fred Brooks said the programmer, like the poet, works only slightly removed from pure thought stuff. He builds his castles in the air, from air, creating by exertion of the imagination. We start with a blank page, and we can create pretty much anything we can imagine. And the things we create can change the world. From Twitter helping people plan revolutions, to the processor in your car working to stop you skidding, to the smartphone which means we no longer have to remember pesky daily details, our programs are everywhere. Our imagination is everywhere. We developers are incredibly privileged. We are truly building the future. It's an extraordinary amount of power. And with that power comes an extraordinary responsibility. How often do we stop to think about that? How often do we discuss, both among ourselves and with a more general audience, what this means? Embedded devices use an order of magnitude more computers than those used in laptops, desktops, and data centers. These embedded computers often control life-critical systems, from power plants to cars to medical equipment. Even a simple central heating control system or home appliance can kill someone if it is poorly designed or implemented. When you develop for these devices, you take on a staggering responsibility. Many non-embedded systems can also do both great good and great harm. Social media can promote peaceful revolution or foment ugly hate. Big data can make shopping easier, and it can destroy any vestige of privacy you might think you have. Banking systems make loan decisions that change people's lives. And just about any system can be used to snoop on its users. We've seen hints of the possibilities of a utopian future, and examples of unintended consequences leading to nightmare dystopias. The difference between the two outcomes might be more subtle than you think. And it's all in your hands. The moral compass. The price of this unexpected power is vigilance. Our actions directly affect people. No longer the hobby program on the 8-bit CPU in the garage, the isolated batch business process on the mainframe in the data center, or even just the desktop PC, our software weaves the very fabric of daily modern life. We have a duty to ask ourselves two questions about every piece of code we deliver. 1. Have I protected the user? 2. Would I use this myself? First, you should ask, have I done my best to protect the users of this code from harm? Have I made provisions to apply ongoing security patches to that simple baby monitor? Have I ensured that however the automatic central heating thermostat fails, the customer will still have manual control? Am I storing only the data I need, and encrypting anything personal? No one is perfect, everyone misses things now and then. But if you can't truthfully say that you tried to list all the consequences, and made sure to protect the users from them, then you bear some responsibility when things go bad. Tip 98. First, do no harm. Second, there's a judgment related to the golden rule. Would I be happy to be a user of this software? Do I want my details shared? Do I want my movements to be given to retail outlets? Would I be happy to be driven by this autonomous vehicle? Am I comfortable doing this? Some inventive ideas begin to skirt the bounds of ethical behavior, and if you're involved in that project, you are just as responsible as the sponsors. No matter how many degrees of separation you might rationalize, one rule remains true. Tip 99. Don't enable scumbags. Imagine the future you want. It's up to you. It's your imagination, your hopes, your concerns that provide the pure thought stuff that builds the next 20 years and beyond. You are building the future, for yourselves and for your descendants. Your duty is to make it a future that we'd all want to inhabit. Recognize when you're doing something against this ideal, and have the courage to say no. Envision the future we could have, and have the courage to create it. Build castles in the air every day. We all have an amazing life. Tip 100: It's your life. Share it. Celebrate it. Build it. And have fun. Appendix 1. Bibliography. Vard Antinian, Jesper Deerhag, Anna Sandberg, and Miroslav Staren. Mythical Unit Test Coverage. IEEE Software. Jackie Andrade. What does doodling do? Applied Cognitive Psychology. 24, 100-106, 2010, January. Joe Armstrong. Programming Erlang, Software for a Concurrent World. The Pragmatic Bookshelf, Raleigh, North Carolina, 2007. Albert J. Bernstein and Sidney Kraft Rosen. Dinosaur Brains, Dealing with All Those Impossible People at Work. John Wiley and Sons, New York, 1989. Frederick P. Brooks, Jr. The Mythical Man Month, Essays on Software Engineering. Addison Wesley, Reading, Massachusetts, Anniversary, 1996. Brad J. Cox and Andrew J. Novobilski. Object-Oriented Programming, An Evolutionary Approach. Addison Wesley, Reading, Massachusetts, 2nd, 1991. Melvin E. Conway. How Do Committees Invent? Datamation. 14, 528-31, 1968, April. Gavin De Becker. The Gift of Fear, and Other Survival Signals That Protect Us from Violence. Dell Publishing, New York City, 1998. Tom DeMacro and Tim Lister. Peopleware, Productive Projects and Teams. Addison Wesley, Boston, Massachusetts, 3rd, 2013. Martin Fowler. UML Distilled, A Brief Guide to the Standard Object Modeling Language. Addison Wesley, Boston, Massachusetts, 2nd, 2000. Martin Fowler. UML Distilled, A Brief Guide to the Standard Object Modeling Language. Addison Wesley, Boston, Massachusetts, 3rd, 2004. Martin Fowler. Refactoring, Improving the Design of Existing Code. Addison Wesley, Boston, Massachusetts, 2nd, 2019. Eric Gamma, Richard Helm, Ralph Johnson, and John 5, Vlisides. Design Patterns, Elements of Reusable Object-Oriented Software. Addison Wesley, Reading, Massachusetts, 1995. Michael Holt. Math Puzzles and Games. Dorset House, New York, 1992. Andy Hunt. Pragmatic Thinking and Learning, Refactor Wetware. The Pragmatic Bookshelf, Raleigh, North Carolina, 2008. T. Joyner. Contagious Depression, Existence, Specificity to Depressed Symptoms, and the Role of Reassurance Seeking. Journal of Personality and Social Psychology. 67, 2287296, 1994, August. Donald E. Knuth. The Art of Computer Programming, Volume 4A, Combinatorial Algorithms, Part 1. Addison Wesley, Boston, Massachusetts, 2011. Donald E. Knuth. The Art of Computer Programming, Volume 1, Fundamental Algorithms. Addison Wesley, Reading, Massachusetts, 3rd, 1998. Donald E. Knuth. The Art of Computer Programming, Volume 2, Seminumerical Algorithms. Addison Wesley, Reading, Massachusetts, 3rd, 1998. Donald E. Knuth. The Art of Computer Programming, Volume 3, Sorting and Searching. Addison Wesley, Reading, Massachusetts, 2nd, 1998. Brian W. Kernahan and Rob Pike. The Practice of Programming. Addison Wesley, Reading, Massachusetts, 1999. Bertrand Meyer. Object-Oriented Software Construction. Prentice Hall, Upper Saddle River, New Jersey, 2nd, 1997. Jerry Z. Muller. The Tyranny of Metrics. Princeton University Press, Princeton, New Jersey, 2018. Robert Sedgwick and Philip Flageolet. An Introduction to the Analysis of Algorithms. Addison Wesley, Boston, Massachusetts, 2nd, 2013. James Ridley Stroop. Studies of Interference in Serial Verbal Reactions. Journal of Experimental Psychology. 18:6436662, 1935. Robert Sedgwick and Kevin Wayne. Algorithms. Addison Wesley, Boston, Massachusetts, 4th, 2011. Nassim Nicholas Taleb. The Black Swan, 2nd edition, The Impact of the Highly Improbable. Random House, New York, 2nd, 2010. James Q. Wilson and George Helling. The Police and Neighborhood Safety. The Atlantic Monthly. 249, 3, 29-38, 1982, March. Edward Jordan and Larry L. Constantine. Structured Design, Fundamentals of a Discipline of Computer Program and Systems Design. Prentice Hall, Englewood Cliffs, New Jersey, 1979. Edward Jordan. When Good Enough Software is Best. IEEE Software. 1995, May. Copyright symbol 2020 Pearson Education Incorporated. I would rather have questions that can't be answered than answers that can't be questioned.